some of these particles, but mostly it will have the air inside. Okay, so this is a typical drying system. The reason why I wanted to show you this, because it is very important, especially in drying applications, how these bubbles behave. Okay, and we're going to talk about this in a little bit more detail shortly. But if somebody says you're working somewhere and you need to propose a dryer, and you say, I think we're going to use a fluidized bed dryer, and your supervisor, your boss says, well, tell me why a fluidized bed. What are the advantages? And you should be able to list all of these that you're seeing in front of you. First one is high moisture removal rate. It it efficiently removes moisture. We talked about this. High thermal efficiency. Remember, the air you're putting into the fluidized bed, you have to spend energy, you have to spend money to heat this air. So how much of it are you transferring? How much of that thermal energy are you transferring to the bed of solids in order to remove moisture? So it's the efficiency of this thermal process is quite high. It's not great, because I'm also going to list it as one of the disadvantages, that the hot air you're losing, unless you use it for another application. It's uniform drying. I told you about, of course, it's the better mix the bed, higher the uniformity of the properties of the particles in the bed. It's fast drying. Relatively, again, examples I gave you, if you were to do it naturally, just exposed to radiation, it will take much longer. However, here, it will be very fast. And of course, the other example, it will never be uniform if one layer is above the other. It will require constant agitation. Bed temperature is steady, stable. So because of the large, again, thermal mass you're creating in there, material transfer is easy. Fluid bed makes it easier for us for having a fluid-like behavior, as we talked about it, that it will obey all the hydrostatic laws. Versatility, again, you can dry wheat one day and the next day you can dry something else. It's all possible within, of course, a prescribed range or particle classification. Low maintenance cost. We touched on this earlier, that because there are no moving parts within the bed, the only rotary piece is the blower that is providing you with the fluidization air. Control is relatively easy, and you will add, you can add some automation to it, which will be required, but you will find out why it will be advantageous to add some automation to them. And it is quite adaptable. It can be integrated. You can remove the moisture on one hand, and you can use it also as a cooler or mixer or coater or classifier in various forms and shape. Okay. Put this here so I'll know my time. What are the okay, the boss said really good. Okay, sounds very good, attractive, but what are the shortcomings? Are there any disadvantages that we should be aware of before we invest some good money into this? And you should be able to say, well, as again, when we We are putting a lot of air through here, and you can easily calculate the amount of energy you need to heat this air to, let's say, 60 Celsius, 65 Celsius, and you're putting through, I don't know, at least a few tons of air per hour. So it costs you money, but then you throw this air out of your at the exit because you need to continue to provide air. So it's a continuous process, whether it's batch or not, but still air must be moved. Generally, solids must be fluidizable with average diameter less than 10 millimeters, okay? 10 millimeters is 1 centimeter, about this size. It's a fair size. Could it be larger? Yeah, but you will run into a lot of challenges. There is something we didn't talk about it, but I am hoping that you're familiar with the term attrition. Attrition is because it's a bed of solids when, especially if they're not perfect around, when they touch each other and they break pieces off each other, okay? Attrition. Therefore, you lose some of your material, or sometimes they touch each other and then they could be fragile and they break into smaller pieces. And if that happens, it's much faster, the terminal velocity, and you lose those, and also you lose the integrity of your product. And because of that, and for a variety of other reasons, you will need a dust removal equipment, usually in the form of cyclones or bag filters, or depends on it. So your boss said that's pretty good. I am convinced. So we're gonna take this to the next level and invest some money in there, and we're going to design and build and operate one. Then you'll need to decide what kind of bed you want. Do you want a batch dryer? Means you will load it, run it, drain it, load it, run it, drain it, or you need a continuous one. So batch dryer, usually if you have the range is not bad, but still a smaller one, between 50 kilograms per hour to 1,000 kilogram 1 ton per hour. These could be also mobile. Okay, you can put them on the back of a truck and take it to the field, so long as you have a diesel engine or engine running and providing you with the rotary function of a blower. You can take it to the field and collect it there. This is suitable batch operated upstream and downstream processes, or when multiple operations, required for granulation, coating, sifting, anything. Airflow and temperature can be minimized again in order to save energy, or you can modify it. These kind of batch fluidized bed dryers, you can also, even though I say mixing is great, it's usually depends on the type of particles. You may not have a well-mixed one. We talked about it. You may want to put some mechanical agitators or other means, like, a shaker, vibrating bed, and things like that. It's a lot easier to apply those if it's a batch operation. And design is relatively simple. See, you have your particles, grain, whatever you want to dry through here. You use, in this case, a little high pressured air because it won't go through it, so you have to kind of provide a pneumatic transport like conditions to push it through here, comes downwards in the opposite direction of the hot air, and they're dried within a prescribed time period, and then poof, you take it out and then put another batch. Continuous dryers, however, which are desired for larger loads, could be in two different categories. One category is the back mixed dryer, and please pay attention to the two. One is back mixed dryer, the other one is plug flow dryer, fluidized bed. Here, this is where the dense bed surface is, okay? And solids are fed into the dense bed, okay? It depends on the density and size and everything, but this is one design that's into the dense bed, and the other one, in this case, plug flow, is to the freebore, okay? And so here, as they are falling, the surface moisture is very quickly removed, and then here inside they'll have more time, residence time, for the inherent moisture to be driven out, and here you collect them. If you have you start with smaller surface moisture, you need your dryer mostly to remove the moisture that's trapped inside the particle. Then you want it to spend more time within the dense bed, okay, and to benefit from all the agitation and mixing and everything inside the bed. So flow pattern, of course, in here differentiated based on the flow pattern of solids in the dryer, and this includes the plug flow and back mix flow. Inlet and outlets, they have an inlet for moist material and outlet for dry material. That's both, we see. So that is the beauty of the continuous operation. The batch one, as I said, you operate, then you stop, you unload, put the fresh batch in, and then you start again. Here, it's continuous. You have one port for material in, and the prescribed time, whatever, and then you take the dry particles out. Viscous or cohesive materials are a lot better handled here, especially if they need pre-drying. A reverse mixing fluidized bed or a continuous back mix fluidized bed is much more appropriate than a batch one. Okay, I'm gonna maybe just spend a few minutes here. These are interesting design. This is pulsed fluidized bed dryer, and it pulsates. Instead of feeding the air continuously, you pulse it, and there are reasons behind that. Pulsation helps break both slugs, but also helps better distribute particles. And also, you have different chambers. Like part of the bed here is fluidized, part of it is not. Particles that are in the non-fluidized part, they are able to, again, because it's still in a hot environment, release or allow for the inherent moisture to move towards the surface. These are a little more detailed, but nevertheless widely used in industry. This is the hybrid one. Again, it has different methods, and part of it is fluidized, part of it is not, for the same reason. Okay. Superheated steam is better for some applications that need to be quite sanitized. So let's talk about things that you love to do and how do you calculate heat transfer and mass transfer in this case. Remember, we're going to see some modeling and calculations and everything. The objective is, I am asking you, I said, I am in continuous need of drying my crop. It will come to you with making it up 40% moisture content. I want you to remove it, the moisture down to 10%, 8 to 10%, so I can then sell it. And you need to calculate precisely how much time you will need, how long they need to be dried, at what temperature, so that you can ensure that the product is at the prescribed level of moisture. Okay, so heat transfer, as I mentioned earlier, hot air basically heats the particle and enables mass transfer. Moisture, again, is removed in two steps that we explained. I explained a little while ago. And then all of these are taking place simultaneously, okay? The removal of the moisture from the surface, at the same time the particle is being heated, the capillary moisture is moving out to the surface and is being taken away, and you're ensuring a uniform environment for it to take place. So, you know, you've taken, I'm assuming again, you know your heat transfer and mass transfer, you know your transport phenomena and unit ops, that the total rate of heat transfer from the bed to either a single particle or bed of particles, let's say a single particle, you need to have the heat transfer coefficient. In drying applications, it is mostly convective heat transfer as opposed to combustion that you have to take radiative because of lower temperature. We're quite comfortable, we're quite fine just using a heat transfer coefficient that is dominated by convection. And we have temperature of the gas, of course, air, and temperature of the particle. And then you can calculate the total heat transfer rate. And for the heat transfer coefficient, of course, you have to know the particle Reynolds number. Particle Reynolds number will give you the particle Nusselt number. Then from the Nusselt number, you have the thermal, the heat transfer coefficient. And this is, again, done in a way that in an almost isothermal conditions, if you can, for which if you insulate the bed so that there is no heat losses in or around the or surrounding the bed, and all the heat is trapped there for one purpose, to be transferred to the particles. Okay, and this is the most general equation you can use, and you have to know the Reynolds number of particles, Reynolds number within the tube or the vessel, which then the characteristic length is the diameter of the bed. whereas the particle Reynolds number is characterized by the particle diameter, and then you use those. The Froude number, Reynolds number, Nuss number, they will all help you to determine the total heat transfer through the estimation of the heat transfer coefficient. Okay. As I said, in fluidized beds, there are no, like, because of the nonlinearity of the whole thing, you have to rely on a lot of experimental data. And that's where, if you're wondering where did these numbers come from, they are all obtained through experimental investigations and data provided in order to obtain these correlations. And the mass transfer takes place in a similar fashion that as I mentioned, you have to drive the moisture out here and then wait until you have the other part moved. This is a constant pressure operation, and I did not mention it earlier on, but it's not a pressurized vessel. It's operates under atmospheric pressure, and for the mass transfer, of course, we use two fundamental equations. One is the conservation of mass. Whatever total moisture goes in, that moisture will go out. So it doesn't go anywhere else. So where does the moisture come from? It's moisture within the particles plus whatever moisture, even though you're going to dry the air, you put in there, and that will equal to the total moisture that is coming out with the exhaust air. And then you apply energy conservation and the enthalpies and masses, and this from the particle, from the air, will be equal to all of these plus heat evaporation. And as I said, if you don't have perfectly insulated, then you will have some losses going out. You have to account for this. Then you can calculate heat transfer due to evaporation in this fashion. Okay, let me catch my breath for a sec. So let's then start looking a little bit closer in more detail. What do we need for this to operate? I need a feeding system. I need either a mechanical conveyor belt system, or I need a system that I will need to aerate for it to move easier. So you'll decide on this one. Of course, you need the main vessel. You will determine that based on, let's say, continuous operation. The load is given to you by the customer, and then that will help you. You do your calculations to determine the diameter. Usually, it's a lot easier if it's cylindrical, or it could be rectangular. Rectangular ones are easier to manufacture because you just weld the plates. So just depends on however you want to do it, but you will then be able to design the size of it. Then here comes one of the most critical aspects, is to decide on the distributor type. Okay. What type of distributor you will need. Remember, we said distributor is essential to provide the bed with a uniform distribution of air and bubbles to provide the best mixing environment, and at the same time support these particles or prevent them from falling downwards when the bed is stopped. So then you need the plenum chamber. Oops, where did I go? It is important. Usually it is shown as empty, but if in your, I don't know, in the lab, if you saw it, and if you have it, we call them Russian rings. It's all uh, used like a grinding machine in ensuring that air entering is already distributed uniformly, and you've taken care of all the inlet losses and whatever, that the air is already entering the distributor plate in a uniform fashion. Then you will design your exhaust system, ensuring that, again, for example, the slope is this of this cone. If you do it this fashion, is important. What kind of angle you will use, and the exit losses here that we take into account. And if you need to control it two ways, you may want to put an exhaust fan in there, but usually you won't need it. And do you need to clean this air? Then you will need gas cleaning apparatus there. Okay, so these are the basic elements of a fluidized bed dryer that you will be thinking of. You'll either manufacture them in-house or you will order them through suppliers. So, as I said, if you have fine particles, they will definitely escape. You may want to either if you're doing this in a plant, you don't want a plant filled with dust and everything. You want it to be in a clean environment. Second thing, you may want to collect those because it's money. You may not be able to sell those at the same price as this intact ones, but you may also still sell it at a discount. So you don't want to throw your money out. And you use, as I said, cyclones, other means to capture these fine particles. You need to, of course, ensure that whatever you do, it will cost you the minimum pressure drop throughout the bed. The higher the pressure drop, the higher the energy requirement for your blower. So make sure that your design will. I mean, you cannot escape the pressure drop that will be needed for the minimal fluidization, and at the upper. Remember, you need that delta P until you overcome the bed resistance. After that, it is flat. So make sure that you're fluidizing in an efficient way. And you will definitely use, even though, of course, there's no stoichiometry involved here, but you will use, the more air you use, the faster the heat transfer rate, but up to a level. When it comes to the distributor, and again, you will ensure that it is providing you with a uniform mixing across the bed. Usual rules when you're doing this, you follow like rule of thumb: 30% of the pressure drop for upward and lateral flow, and 10% for downward flow distributor plates. You will also, you're not just doing this from the scratch. In a fluidized bed, it's a through flow fluidized bed. This is basically like evaporation rates. It's depending, of course, what you're trying, but so you can reach up to, like, this is, of course, sorry, it's in British units, but quite high evaporation rates you can achieve. So you know that you're working within that window. So I want to talk about slugs. And why do I want to talk about slugs here? This is a bed. We call this is freely bubbling. You have bubbles formed at the distributor, just right above the distributor plate, and they start moving upward, and some of them will coalesce with the other. Normally, they will grow in size. In certain cases, they won't, but then depending on the size and of the particles and size of the vessel, and we talked about this, they may coalesce, they will join, one will join with the other, and then will form a slug. And then when the slug is formed, your bed is basically defluidized, and we will see this shortly. Why am I saying this? I want to take you back to a Geldardt's classification, okay? And here, look at the particle size in micron. And we said we have mostly grain around 1,000 micron, and this is the density. And it is quite possible that you will be in a spottable region according to Geldardt's classification, and that your particle will be a group D particle. Okay, so look at all these. These are all experimentally obtained. Look at these. For example, let's see where rice here, for example, here, rice. You see, it's here, but if you want like big S, it's right here in the spottable region. So you have to take this into consideration very seriously. So most likely, they will be group D particles. Every drying application that I have involved or designed, they fell into the group D particles and larger than around or larger than 1,000 micrometers, and that's the case. It is a spottable application or particle. Very dense particles, in addition to the size, can also be characterized as group D particles, even though they could be smaller. Okay, like in iron ore, for example, processing, that will be the case. So, if that is the case, it limits mixing. Why? Let me take you to this video. So, I'm going to show you one more. Okay. As you saw in the video, short video, when the bed spouts, you saw the core place where a lot of convective air movement is, and convective heat transfer, mass transfer are taking place. And around that, it is like almost like a fixed bed. and particles are moving very slowly. So, as I said, in certain drying applications, you may want to use a spot bed because um, you need to keep the particles longer, the grain longer in the bed, but not necessarily subject to the airflow. So you provided airflow in a way that it's only enough for the core, but it's not needed surrounding, so that they could stay there longer and have the moisture removed through diffusion. Because doesn't matter, and once they reach that stage, how much they are exposed to the air. So that is the case. In some cases, however, you don't want a spouted bed. You want a uniformly mixed one. So you have to be careful, mindful about the size of the particles and the group of the particles. And if you don't want a spouted bed, you will take some precautions like controlling the air, but also you may want to put some mechanical lures and other means by breaking those spouts up, then into smaller bubbles, and then promote more mixing. Okay? So for that, you will need to figure out the minimum slugging velocity. This is the simple correlation that takes to account the particle, whether they're spherical, cylindrical, so the shape factor is important, and then the frequency of slugs. You will need to know how frequently they form, and with that, you will be able to calculate a minimum slugging velocity. Okay, how about a break? It's been an hour. Let's take a little break, 5 minutes again, and then we'll reconvene. Okay? Then we'll talk about distributor plates. Okay? All right. Yes, you are. So we can start. Thank you. Okay. Remember what I just said before the break that um, uh, we may need to um, um, ensure that if you don't want slugging, then we need to take action to break the bubbles or break them up or use better, induce better mixing. So the upper part of this page, you see this is just a typical conventional distributor plate. You have these holes, and then you put these tuyers in various fashion. It could be just straight flow out, or you could do a bubble cap here, and then push it out, and then put this top here, though, that the air will go in the radial direction. Or if I wanted to induce some shear flow, and that will help me break the bubbles up and also push the particles in a rotating fashion as opposed to going straight up. We call it a swirl plate. We put these nozzles to yours, but instead of going straight up or straight this, we'll give it a tangential angle, and with that you create another dimension and causes twisting action. We call it swirl. So is it beneficial? Let's see. We try this in a lab, and you don't need to be concerned about, but we measure the power spectral density of pressure fluctuations, and here is power spectral density. This is the frequency. This black dotted line is with a straight plate, whereas with swirl plate, you see this amplitude smaller. That means we have achieved that makes, instead of just air going straight out, it is well distributed in the tangential and radial direction. And also autocorrelation of the pressure fluctuations is represented by, again, by this red or pink, whatever color you're seeing here. There's another color here, but it's very faint. But this is, again, showing that by using that kind of plate, we can achieve much better mixing and also prevent slugs from happening. My question to you is, this is really good. Why don't we use this all the time? There's a price you have to pay for it. I mean, yes, it is more expensive to manufacture, but also it will cause higher pressure drops. So you'll have to take this into account. But nevertheless, the benefits of using that kind of distributor plate outstrips the cost in manufacturing and operating such bed. Okay. The next thing we need to be mindful in drying applications is the effect of moisture content of the particles on the hydrodynamics of the bed. Why is it important? We briefly talked about this. If you have dry particles, your minimum fluidization air is the amount of air, the drag force that is required to overcome the gravity, okay? It's not the case when the particles are wet. But what kind of wet or wetness are we talking about? It could be in three different fashion. It could be, we call it a pendular state, that most of the particles, they are like in contact. In funicular state, that you have these parts filled with moisture. And this is the capillary state, that it is a lot more pronounced. Depending on which one, then it will affect the amount of force you have to exert on these particles in order to break them apart. So this is the case. As I said, if it's usually we look at the drag force, and the moment the drag force is larger than gravity, we mobilize, we fluidize the bed, we achieve minimum fluidization. Of course, buoyancy is, as I mentioned, becomes important if it's a liquid bed, but we're not talking about liquid beds. So in the case of wet particles, we have an additional force here. We call it the binding force, okay? That is the force that is holding these particles together, okay? Adhesive or cohesive. So your force balance then will be drag force and buoyancy, and it will be equal to gravity and binding. You have to take. So binding forces, you have two types of it. One is the van der Waals, we call it force, which is the cohesion force, and the capillary action force is the adhesion force. So they have to, they'll all be together in the form of binding force, and it has to be taken into account, okay? The minimum fluidization velocity, in this case, will have to be higher, okay? Because your drag force will have to also overcome the binding force. I can give you later on, I think, how to calculate that minimum fluidization velocity for different kinds of, there are different correlations available for different types of grain. The thing is, as a designer, you will, as I said, you rely on a lot of experimental correlations, but there is a lot of value behind modeling aspect. So if you properly model, you can mimic those experiments through computer or CFD modeling of the drying process. To be able to do that, you need to understand which group of particles you are building your mathematical model. If it's a group D, most of the gas is in emulsion phase. Bubbling is velocity is smaller than incipient velocity. Minimum bubbling velocity is equal to the minimum fluidization velocity. That means as soon as the minimum fluidization is achieved, bubbles form and they grow to larger size. They start small. As they move up, they grow. Why am I saying this? When you're modeling this, you have to take this growth into consideration. If it's a group B particles, yeah, bubble size increase also with height, but if it's a group A particles, bubbles remain constant. Therefore, you don't need to take another variable, put another variable into your model that will also make the solution or conversion very difficult. And group C particles, the channeling is one of the things that you will need to take into consideration. So in modeling, you have to make some assumptions. If you're building a coarse model, then you assume a mean bubble size. It's contrary to what I just said, regardless of say the bubble size remains constant in the axial direction, or you say that bubble size, variable bubble size in the axial direction only, but in the radial or this axis, it remains constant. In the most complex one, both axially and radial lateral direction, the bubble size changes, and you have to have it in both dx, dz direction. We covered these earlier on. That to begin with, you have to have all the hydrodynamic parameters well figured out before you embark on the modeling. I want you to recall the drying process because you need to incorporate this into your model, that you have two periods of drying and you have to, each will have to be modeled differently. The falling rate period, the solids experience a set of complex processes during the falling rate period. And the average moisture content of, let's say in this case, wheat particles at any time can be obtained by integrating over the grain volume. Okay, so it's a complex thing, but nevertheless, you need to go through a lot of diffusion constant and everything in order to calculate this one. Constant rate drying, the rate is constant because it is, you know, the difference now. The diffusion type equations, you don't need to do this. You don't need, you can neglect, you can ignore the diffusion side, because during constant rate, the amount of moisture removed is much, much higher, larger than the amount of moisture that is going to the surface through diffusion. Okay, so that is the solution. As you can see here, is much easier, but you have to bring them together nevertheless in your model. So if you successfully model, you can you also see that drying rate for a given particle across time, you can model, you can find it. Why am I saying this? Because when we do the modeling, and you can, within again parameters, you say, hey, I'm going to take bed temperature at 40 Celsius, and then you can figure out how high the drying rate is going to be over time. Okay, you see the two periods, by the way. Okay, fast and then slow. And if you bring the bed temperature higher up, it will be higher, and then in this case the highest. So higher the temperature, the higher the drying rate. But as I said, you are not, you don't have the complete freedom in choosing that temperature, because you will be hurting the integrity of the grain if you go beyond a certain temperature. And again, this is again normalized moisture. As you can see, the higher the temperature, the faster or higher the drying rate again. Okay, when you model it this way, you can really, then you'll have a very good idea about what temperature to choose and how long, especially here, you need to expose the grain particles. Say if you keep them for 20 minutes, okay, you achieve this. And if you keep it for 60 minutes, the difference is very, very small. So for that, we will see what we can do about those. Again, very clearly you see different loading and different drying rates can be easily calculated. So the question is then, okay, I have successfully designed a fluidized bed dryer. And here I see that if I keep these particles of grain being heated, I'm throwing my money out. Yes, there is a moisture removal, but how long should I do this? Then you're concerned about the thermal efficiency of the process. Let me go ahead. Thermal efficiency is simply energy transmitted to the solid. How is this energy transmitted? Is by heated hot air. Okay. And how much of it, I'm sorry, how much of this heat is transmitted to the solids? And how much of it provided into the bed? Okay, so that will give us the thermal efficiency. So let's go back here. I'm going to go here. This is the blower that will give us the air. If the atmospheric air, depending on what part of the world you are and what time of the year it is and all of those. So the relative humidity of the air is very important. If you're in a very humid environment and the relative humidity of the air is like almost 80%, 90%, you're introducing a lot of humidity, and your ability to remove moisture from the particles is very small. You'll reach saturation very fast. So you may want to remove that. Okay. So dehumidifiers will be important. Of course, you have a dehumidifier. Usually it requires a cooling process, a condensation process. It will cost you again. So you have to understand the cost benefit analysis. Then you have to filter it, make sure that depending on the application, the air you're putting in is also clean, safe air to put into your dryer. Then you heat it and put it through. And this air, normally, if you don't take any precautions, you're throwing this air out. How about if I recycle some of this air? If I recycle some of this air, I'm introducing air back into the bed at higher temperature. Okay? It's because it's at high temperature, not higher temperature, but nevertheless, its temperature is higher than the ambient air. But remember that air is also laden with moisture. So understand that if you increase the recycling, you're definitely increasing the moisture content of the air. It's going out. But if you do this in a cyclic way, so that you introduce, recycle some of the air, stop, recycle again, that will optimize the moisture removal process. This is a very, very critical to increase the thermal efficiency. You can program this through your mathematical modeling, and then feed it into an integrated circuit that will control the valve here and the fan here and recycle it appropriately. So as you can see here, the percentage of recycling, if you do that 30% is here, but it exponentially almost grows the more you, but of course you cannot fully recycle it. It's supposed to be very efficient, but then you are introducing a lot of the moisture back into the bed. The second aspect is intermittency. That means you operate the bed and you shut it down. Okay. You operate it for, I don't know, 15 minutes, shut it down, 20 minutes, you start again. Every time you do this, it's your drying rate is affected. By doing that, all you're doing is those stubborn inherent moisture that is trapped in the capillary, you're enabling it to move to the surface. It's going to happen whether you put tons of air over it or not. It is completely independent of the air. So why should you fluidize the bed while you're waiting for that moisture to move out? So you wait for it, you know when it's gonna maximize, and then you operate the bed again, slump it, operate it. And when you do this in combination with the recycling, you achieve the maximum thermal efficiency. Okay, I oversimplified it, but this is how modern dryers operate. What are the challenges? Scaling laws, you need to be able to scale it from lab to application. Erosion and agglomeration will change. So here are a large number of design and operation considerations. I'm going to go over them quickly. We talked about swirling. It definitely benefits increasing the bed height or particle density decreases the effect of swirling. So if the shallower the bed, the better the swirling effect naturally. If it's too deep, this swirling effect will not reach to the top. Moist particles, we talked about this. You have to make sure that you have a good idea about the moisture content that will help you calculate the minimum fluidization velocity of wet particles, and that you will be able to break that bridge. We can again, the correlation, we can find it in literature. Which ones will we talk? Gas velocity. Yeah, we talked about gas velocity has no significant effect on the drying rate of the materials in the falling rate period. That's why we design different kinds of beds with partitions sometimes, or intermittency. Heat and mass transfer, we saw how can be done. You increase the temperature, definitely. You increase the gas air velocity, definitely. But up to a level, you don't want to lose particles, or you don't want to hurt the integrity of these particles. Recycle. I'm sorry. Okay, I will continue. Okay. I did not mute myself, but my computer decided to mute. So it's unmuted. My computer is saying that you've talked too much. It's time to stop. So, okay. Just wondering if there are any questions regarding this, or the questions I left with you yesterday. Any questions? I will try to answer. Again, it depends on the operation, but definitely for large scale, and especially if it's in a combination with power and heat, an IGCC process, for example, definitely circulating fluidized bed is superior. Bubbling fluidized beds, they were the early stages. But if I am again dealing with a small load, like the rice husk example I gave, and for a smaller scale operation, it's much better to use bubbling bed, because it is easier to design, manufacture, and operate. It depends on the case, but if you extend the scale amount, it's definitely it will have to be a circulating bed. Mm, mm. Did you say slug formation? I'm sorry, we are gasification. Yeah. Um, if you um, rapid heating minimizes it, won't stop, but you'll have much less amount of tar. Tar formation is unavoidable. It will happen. If you do it slow heating rate, you'll have more. Higher heating rate, you'll have small. But for the end use, you will have to remove it. So tar will form. It's the key thing is what kind of measures we'll take. Usually you condense it on a surface and remove it. But how much of it will form depends on the heating rate. Okay. Like that, I'll give you one example. One of the early on, I did it once and then decided not to proceed. When you fry food, you either use olive oil or vegetable oil, whatever, but after a while, it reaches a point there you cannot use it anymore. And what do you do with the waste oil? So we used again a process to regain these as fuel, and it was disastrous because the diesel engine got gummed up with tar, and it became unusable. So with gasification processes, it will have to be very carefully controlled, especially if you're using gas turbines in combination with that process. Yeah. What kind of risk did you say? I'm sorry. Oh, um, um, basically, whatever it is. I mean, for large power plant type of operations, you have either coal or natural gas. If you have abundant amount of biomass, of course, that is also, I mean, Sweden, for example, they use it successfully, but most utilities they do it from natural gas or um, um, coal. Okay, and the idea is to minimize the amount of carbon dioxide emitted to the atmosphere environment per megawatt, megajoule, whatever of energy produced by uh, through gasification, you have much smaller amounts of carbon dioxide in that process, but you improve the efficiency of the system by combining it with uh, heat and utilize that heat somewhere else. Therefore, per unit energy produced, you have much less carbon dioxide. Yes. Mm. They said kiln dryer. Yeah. Uh, Very simple. The others, they have rotating parts, okay, moving parts. They are more, you need more power, more energy to operate them. They don't give you the same versatility as fluidized beds. Uh, so, but with though the others, you can put a lot higher heat and you can achieve much higher drying rates, but it is more expensive. As I said, fluidized beds, they are easy to operate up to a certain point, like for grain, agricultural products, byproducts, and all of those. It's much simpler and a lot more techno-economically feasible. Okay, I won't use the word better, but techno-economically feasible, more feasible. Yeah. Okay, well, thank you very much for your questions and for your attention, and we'll have the last class tomorrow. Okay. Okay. Have a good day.
यहाँ बैठ सकते हैं क्या? बैठ सकते हैं। वो क्या ना कैमरा ब्लिंक होता है पीछे टीवी में। अच्छा ठीक है, बैठ जाएंगे। ये वीडियो है। हाँ ये वीडियो है। नॉर्मल वीडियो का है, देखिए ये डिफरेंट वेलोसिटी में है। एक एक करके वो अलग अलग करके उसका था। तो डाउनलोड हो गया क्या? नहीं डाउनलोड नहीं ले रहे हैं इसको। नहीं तो लैपटॉप में देख रही थी ना वीडियो।
मतलब एक बार एक वीडियो है पीपीटी में रखा गया है।
नहीं हाँ पीपीटी नहीं। हाँ पीपीटी
बट ये डाउनलोड नहीं हो रहा।
ये वाला वीडियो है तो पीपीटी में होगा तो वो तो चालू हो जाएगा ना।
हाँ वो दिखाना है ना बबल।
तो लेक्चर अनदर ये वीडियो को।
ओहो
ये डाउनलोड नहीं हो रहा।
ये तो गूगल स्लाइड्स
ये कर लो तो अटैचमेंट रखते हैं खोलो। हाँ
नहीं लेना डाउनलोड।
गूगल ड्राइव पे रखते हो। हाँ था जो उठ भी था और वो डिलीट कर दे।
तो ये खुद सिलेक्ट करना पड़ेगा, नहीं तो
हाँ,
क्रिएट
yes.
फोल्डर कर ले।
कर दो।
individual to everyone who can see DS
ओके
ठीक है तो गूगल ड्राइव खोल वहाँ
गूगल
से।
ड्राइव में
उसका नीचे हाँ DS में
वो डाउनलोडेड ही था। इसका एक्चुअली बटन
सेपरेट सेपरेट हाँ नीचे तले अच्छी गोटे गोटे लेख तो सीट गोटे मुझे देखी कर लैपटॉप रे रन कर एक्चुअली अनुप ही पठे थरे लास्ट सेकंड थर्ड लास्ट देखिए तो गोटे शॉट
करते ही देखो
क्लिक करो ये जो लिखा है वेलोसिटी नहीं है
ऑलमोस्ट अभी हुआ है उसका ये कर
क्या
क्वांटिटी
अभी चालू हो गया।
उसको ऑन कर जो डाउनलोड
रीसाइज है।
अभी डाउनलोड हुआ है ये फुल वीडियो।
ओह अच्छा
वो डाउनलोड
इनवर्स हाँ ओपन
बस ये फुल डाउनलोड
ये टाइम ले रहा है शायद ना।
वीडियो है ना इनेबल एडिटिंग प्लीज। full screen चाहिए
ଏବେ ଦେଖ ଲାଗିతే ତଳେ ଦେଖଉଥିଲା ବାହାରେ କ୍ଲିକ୍ କର
ये वीडियो वीडियो
नहीं देखिए
हाँ
फिर इसको पॉज कर दीजिए
अच्छा इसको शेयर करने से कैसे
वेट
ट्रायल कर लेते ड्यूरिंग क्लास हम दिखाएंगे
अभी
पीपीटी मैम दीटा खोला अछि
हाँ
एठी
गोटे लेक्चर अच्छे हाँ
एटा लेक्चर टाको काढले
हाँ
आपण फुल स्क्रीन करले
जॉइन करछि गोटे खाली शेयर करा को वीडियोटा देखिया नहीं लेक्चरटा तो मु कर देबी किछि नहीं वीडियोटा शेयर करिया
शेयर स्क्रीन करे
वही में जो
मिनिमाइज करा को अच्छा
टीम्स में
एमएस टीम जॉइन करछि ऑलरेडी
हाँ
शेयर
विंडोज भी कर सकते हो विंडोज कर देना इधर
हाँ विंडो देखिए
हाँ तो ये आप शेयर कर रहे हो
आपका
already।
जब होगा पेन मैम हाँ एटा जेतो फुल स्क्रीन रे अछि एंते अछि
स्केप हाँ सेटा तो स्केप कर देले
यहाँ पे
एठी जाएगी एटा क्लिक करबे क्लिक करके फुल स्क्रीन
यहाँ
एठी आछि
एक एक के सामने नीचे आ जाएगा
थोड़ा फ्लैट हो रहा है थोड़ा
इसके नीचे आएंगे ये वाला भी चलेगा और थोड़ा ऊपर और थोड़ा ऊपर
आगे ऊपर
और फिर ऊपर। अच्छा नहीं तो इससे
पूरा
कर
आना
सकते
चाहिए
हैं
ना
नहीं कंटिन्यूअस नहीं इटा सेपरेटली आई हैव टू क्लिक मीन एट द डिफरेंट वेलोसिटीज
Wait, right, एक सेकंड एक को ऑन कर प्लीज और व्हाटएवर
इसका नहीं
छाड़ दे सेटा स्टैटिक कंडीशन जे देती सेटा
इससे
छाड़
आप
दे
चेंज कर
हाँ
सकते हो
ठीक है हाँ ये हो गया
ये वाला मजा
हाँ
ये वाला मजा
हाँ हाँ नहीं ये तो सेकंड है लाइट थी वाले बोले
वो जो ये एरो है
एठी
ना,
एठी
ये एरो नहीं हो रहा है ना
नहीं उसके बाद एठी गोटा हो जाओ देखो ठीक है
हाँ
हाँ ये लेफ्ट अच्छा ठीक है सेटी क्लिक
इसका
कर ले हाँ
तो नहीं है।
हाँ
इसका
हाँ इसका नहीं है वो स्टैटिक कंडीशन है उसका वीडियो नहीं है फिर एटा खाली लास्ट
हाँ
हाँ
सब
एटा को क्लिक कर ले
हाँ।
सास जो
अच्छा ठीक है
आप इधर आ जाओ
हाँ
It is taking time to activate it. Meanwhile, you people are carrying on more time. Okay. You will activate it or not? I'm doing that only. आज तो कैमरा ऑन नहीं होगा इधर भी मैम कैमरा इज ऑफ है कर दो जी मैम स्टार्ट कराओ बोले
कहि दियो ओहो फर्स्ट स्लाइड टा कोड पळेला टाइटल थिला हाँ ठीक अछि ओके so good morning everyone am I audible so today we are going to discuss on the inverse fluidization and its application for the treatment of the wastewater. Now, as all of us know that our earth surface is covered by 71% water, but only 3% fresh water is available to all of us. Oh, microphone is muted, mine is showing that. Okay, let me. Huh. Oh, okay. Okay. Full screen I am doing. Slide show. Oh, yes. Slide show. Now it is full screen. Yes. So here as 3% only fresh water available to us, and it is also second things which is most required after the air for all living organisms or living beings on the earth. And the water which we after uses we generate, that is means in the different sectors, there may be domestic sector, commercial, agricultural, or the transport sector. So whatever after use are generated, that is the wastewater. And excluding the domestic sector, the water generated in other sectors are known as the wastewater or the industrial wastewater. So we can call in the wastewater which is generated in the domestic sector as the municipal wastewater, and in other sectors that is the industrial wastewater. As these waters, industrial wastewaters contain various toxic and hazardous pollutants, and they contaminate with the surface water as well as the underground water. So that's why our 3% fresh water also getting contaminated due to our day to day activities and due to the industrial wastewater being that is discharged to the ground without being treated. So thus it is required to treat them before discharging, and this treatment should be proper, by which the toxic or the hazardous pollutants, it may be some organic, inorganic substrates also, it should not be mixed with the water bodies. Now otherwise there will be health issues will be there, shrink in the food productions, and the it will environmental issues also will be there. So that's why it is required to treat all these not changing. Okay, here first let me stop share and share it again, because the slide is not changing. What happened? Yes. So here when we are going to treat this wastewater before discharging into the main water bodies, what parameters we should consider during the treatment of this wastewater? The parameters such as BOD, biological oxygen demand, chemical oxygen demand, total organic carbon, and certain metals or the microorganisms, inorganic nutrients, it may be nitrogen, phosphorus, sulphate and many more. These factors should be considered during the treatment of the wastewaters, and depending on the type of the pollutants, different methods are being used to treat this industrial wastewater. Typically wastewater treatment methods are categorized in three levels, that is primary and secondary and tertiary types, which consist of the different physicochemical and biological methods. Now secondary and tertiary methods are the known as the advanced methods, and example absorption, adsorption, ion exchange, membrane based separation or the biological processes, where the primary method, primary category is the conventional methods will be used. Now among these these biological unit processes is gaining popularity since early 80s, and we where we adopt the technologies to remove these suspended solids and inorganic organic sulfates, ions, and also soluble and colloidal organic matters from the industrial wastewater. And these processes use a great variety of the reactors, including batch reactor, complete mixed reactor, plug flow reactor, packed bed reactor, fluidized bed reactor, etc. Now, the fluidized bed biofilm reactor, which may be aerobic or anaerobic type, are also used under this secondary type of the treatment. Again, it is not getting shared, I do not know. Second,
Click करो just. Click करो भी हो.
by hand I was doing. Okay, let me. I don't know why it is not. Okay, let me see. Share. Today I am facing this problem. Last two classes there was no problem. Share. What happened? Not sharing, not changing slide. Slide show. Okay. Correct. Okay. Now among these reactors, this fluidized bed biofilm reactors, that is aerobic biofilm reactors, use the fluidized bed technology, and that is being currently used or in the recently being in the use for the treatment of the wastewater. Now this aerobic fluidized bed biofilm reactors is known as the inverse fluidized bed reactor, and here the different the industrial wastewater containing the different pollutants are being handled and treated, by which this pollutant level is decreased to a great extent, which we will discuss with some case studies. We will discuss in this 1 hour lecture. Here normal 3-phase fluidization systems, the liquid is usually taken as the continuous phase, where the it may be the co-current or the counter current. Usually the liquid which is the continuous phase, it flows in the upward directions, co-current upward flow of the gas and the liquid, and here the particles are usually denser than the fluid being used, whether it is the gas or the liquid, and the upward flow of the gas and liquid which counter the net gravitational force of the particles with which the fluidization takes place. But when the density of the particle becomes smaller than the density of the liquid, the fluidization will be carried out in the downward direction, because when the lighter particles are used, the movement of the particles will be in the downward directions, liquid flow downward directions, which is in the counter current to the upward flow of the gas. Gas is supplied from the bottom, liquid is supplied from the top, and the lighter particles initially remain on the top level, but with the increase in the flow rate, the solid particles move in the or fluidize in the downward direction. This process will be known as the inverse fluidization. Again slide is not changing.
देखो सेंसी रखा तो फुल स्क्रीन करंतु नहीं से पेन चेंज.
Okay. Again let me check again, because slide is not getting. So let me say just show the inverse fluidization some videos. then you can know. After that again we will see, perhaps the video is open for which slide is not changing. Let me show the video first. Here you can see the first figure, it is shows the static bed, that is when the inverse fluidized bed, the liquid is the that is column is filled with the liquid and some solid particles which is lighter than the density of the liquid. Okay, just no, not net. Okay, just 1 minute. Let me. This one. Okay. Okay, let me share this again. The first figure shows the static bed, that is it is not fluidized in this case, just bed materials forming a packed bed, all the particles remaining on the top of the bed, as it is as all the bed materials are lighter than the water or the liquid. And the second case, we can see the video where here we can see how the materials getting fluidized. Here you can see when we increase the flow rate of the air, because water flow rate is maintained adjusted to maintain the steady state, because whatever the water will be flowing through the inlet, that maintaining the level of the water in the column, some water will be discharged through the outlet. So, inlet and outlet flow rate are adjusted to maintain the steady state in the column. Now, by increasing the velocity, how you can see in the this second case, first case was the static bed, second case the materials was fluidized, but in the lower part you can see the some space is there, that is a thin layer of the particles are found in the lower part, but in this video where the second part, it is almost covered. All the particles covering the entire section, entire height of the column, the particles are entire height of the column is covered with the particles, or the particles are covering the entire height. You can, that means particles are getting fluidized all along the length of the column. And if you last figure, if increasing further the velocity of the fluid, that is the gas, we can see, because water flow rate here we are not varying, just I don't know again. Yes, you can see here more vigorously as velocity we are increasing, more vigorously particles are getting fluidized. Just this is just a short video for the fluidization of the particles in the downward directions with the increase of the velocity. Now, let us move to the our slides which will let me share the slide again. So, just in this as gas flow upwards, the solid particle and this gas which flows upward, this exerts some pressure on the particles and water flows downward. So, because of this force, net force on the particles, particles tend to move downward, and again because of the tendency of the lighter particles to move upward again, the particle also moves again with once again when it is subjected to the force exerted by the buoyancy force by the water and net force of the water and the air, particles float down also. So, thus there is always movement of the particles in the upward and downward directions. Here we can see just a schematic diagram of the co-current and the counter current inverse fluidized beds. Here we can see in the first figure which is on the left side, counter current means the water is flowing from the top, allowed to flow from the top, gas is allowed to flow from the bottom. Here you can see initially before starting the increasing the velocity, all the particles remain on the top level, then gradually when the velocity is increased, then the flow rate of the water is increased and the gas is also increased, the particles tend to move downwards. This is counter current because movement of the water and the gas is there. In the second figure, that is co-current flow, here gas and liquid all are supplied from the bottom, and liquid flows out collected or the outlet is from the side of in the top region, and gas outlet is from the top of the column. Here also the accordingly the flow rate is adjusted, so that the at what rate we need the fluidization, because for the biological action the vigorous movement is not desirable. So, for depending on the type of the applications, we may have the vigorous movement or the smooth movement of the solid particles in the bed. Here slide is not moving today. Okay. Slide, so let me see, and from the current slide. So, here we can see that there are many advantages for this inverse fluidized bed bioreactor, which we use for the treatment of the industrial wastewater in terms of the BOD, COD, total organic carbons, and also that is removal of the ammonia, nitrogen, phosphate, sulphate, phenol, or other toxic pollutants, that is like hexavalent chromium, and that is phenol, etc., can be removed using the inverse or can be degraded using inverse fluidized bed bioreactor. It has advantages that such reactors are compact, efficient, with a small floor area requirement and the low energy consumption also, and higher biofilm surface area is provided with the bed materials, and high mass transfer rate and higher biomass age also, as smooth fluidization is maintained. So, here biomass and also with the continuous supply of the wastewater, the biomass gets the feed continuously, because of which the biomass age also higher in comparison with the other bioreactors, as well as these reactors are also resistant to the toxic loads and the temperature variations. As it is wastewater is taken, so sometimes during the operations sudden temperature rise if occurs in other bioreactors, there the microbes may die. But here, as it is wastewater is taken considered as the main medium. So, here if sudden rise in the temperature is there, that is taken care of by this water, wastewater. As a result, the overall temperature does not rise suddenly, and where the microorganisms, that life of the microorganisms is not affected. These reactors are also used to have larger degradation rate, higher organic loads uptake capacity, means high level of the high concentration of the pollutants also can be degraded, and where degradation rate is also high, and construction cost also very less and do not show any clogging problems. As you from the video you saw, there is no complex arrangements by which there is no clogging problems also, whereas other reactors the clogging problems will be there. Applications, it is mainly used to treat the wastewater, industrial wastewater, the collected from the different industries such as brewery, starch, textile, sugar, steel, dairy industries, also various other wastewater such as municipal wastewater, which contains the inorganic, organic pollutants and harmful industrial pollutants like aniline, phenol, sulphate, ferrocyan, ammonia also they can be degraded using these inverse fluidized bed bioreactors. And dimensions, the reactors with varied dimension configurations also have been used under different operating conditions. Depending on the quantity of the wastewater to be handled, the dimensions can be varied also. And treatment removal efficiency also found to be dependent on the hydrodynamic features of these inverse fluidized bed bioreactors, and what type of the microorganisms we are using, and nutrients present in the wastewater, that is pollutant present in the wastewater, and concentration of the level of the pollutants present in the wastewater. So, accordingly reaction conditions can be maintained, that is the pH level. Reaction conditions mainly refers to the pH, what pH we have to maintain such that the microorganisms will live longer. Now, wastewater categories, as we told that industrial wastewater, whatever the water generated after uses in different sectors excluding the domestic sector, that is the industrial wastewater. And if we consider the domestic sector, that is municipal wastewater, so all are the wastewaters, that is water generated after uses. So, this industrial wastewater can be categorized in 3 groups, that is physical, chemical, biological, 4 groups, that is physical, chemical, biological and radiology, depending on the characteristics, which may be physical, chemical, biological or radiological characteristics. So, physical characteristics include the total solids, that is volatile, fixed, suspended, dissolved and settleable solids, color, odor, that is physical characteristics, the solids having the physical characteristics, they are referred to as the wastewater of the physical in nature, which are these physical characteristics are to be handled or the treated. The chemical characteristics, where the various organic and inorganic components will be present, and organic constituents comprise carbohydrates, fats, oil, grease, pesticides, phenols, proteins, surfactants and some volatile organic compounds also. And inorganic constituents may be alkalinity, chlorides, heavy metals, nitrogen, phosphorus, pH, sulfur and some other toxic compounds, whereas biological features include various microorganisms which may be aquatic plant or animal based and aquatic bacteria and viruses. Some of the microorganisms may be pathogenic, which is also harmful in nature, while some degrade the organic content of the wastewater also. And the sources of the radioactive, that is radiological characteristics, that is because of the radioactive wastes, which these radioactive waste include the mining and of the radioactive materials and those generated from the nuclear power plants also. So, depending on the waste generated from the different sectors, these industrial waste categorized in these 4 categories. Further, here the US Environmental Protection Agency also they just categorized this wastewater into mainly 3 categories, that is conventional, non-conventional and priority types. Whereas conventional types they treat the conventional pollutants like BOD, total suspended solids, pH, oils. Oils may be from the mineral sources, animal sources or the vegetable sources. And non-conventional pollutants which include total organic carbon, COD, fluoride, hexavalent chromium, ammonia, nitrate, the phosphorus, manganese, phenols and sulphate, etc. There are also 129 numbers of the priority pollutants which are reported in literature. So, which are so vast we are not discussing. So, just to have the idea, as per the US Protection Agency, that is there are 3 types of the that is wastewaters are there. Now, coming to the just literature, so in short we will see literature, then we will go to the case studies. Here we can just see that when the density of the particles is less or the close to the that of the liquid, the inverse fluidization is possible, and it is because of the upward gas flow and the mainly the counter current inverse fluidized bed is used for the treatment of the wastewater. And here again for this for proper fluidization to be carried out, we need to maintain the particular velocity, means we need to know the proper velocity at which properly fluidization will be carried out, and also gas hold up, phase hold up, etc. So, this when the fluidization is smoothly carried out and all the particles are fluidized, and that particular velocity will be referred as the minimum fluidization velocity. Separately one can know that what is the minimum fluidization for the gas and what is the minimum fluidization for velocity for the liquid or the water also. And we may have the turbulent fluidization also, but depending on the applications. For the bioreactor, when we are will be using microbes after culturing the microbes, then for that we need the smooth fluidization, not the turbulent fluidization. So, initially when we start increasing the flow rate, as we saw in the video, the entire bed that is the concentration of the solids will not be uniform along the entire axis of the bed. High concentration of the solid will be there near the that is liquid distributor, that is in the top of the bed, and with the further increase in the velocity, solid hold up will be uniform throughout the bed, as in the video we saw. Now, the successful design of this gas liquid solid fluidized bed systems depend on the accuracy prediction and the fundamental properties of the systems. Now, as we know that this accurate prediction of these fundamental properties, such as the gas hold up, pressure drop across the bed, minimum fluidization velocity, bubble size, bubble rise velocity, friction factor, voidage, mass transfer coefficient are some of the important factors. But here for the inverse fluidized bed, will be considering few factors, that is in addition to these phase hold ups, also we need to know what is the that is aspect ratio and settled bed volume to the reactor volume ratio, all the also, and retention time also we will be discussing also. And both here inverse fluidization can be made easier by small density difference between the fluid and the particles. So, there as per the researchers, we can researchers predictions of the Reynolds number and the Archimedes number. So here other researchers also carried out, mainly Fan and Fan et al. In 1982 suggested three type of the models to determine the, that is phase hold ups, and also to know that how they are dependent on the gas velocity and liquid velocity. So, different researchers also further worked on this, and they also added to some modified some these equations and also or correlations, and some of these are just we are summarizing. Detail these correlations we are not discussing because it will take time, we will just case studies we will be discussing. Here the, as I told, that is main is the phase hold up, where the liquid hold up, gas hold up and the solid hold up also we need to know, and also hydraulic retention time, biomass support particles, what type of the support particles we are considering, and bed aspect ratio, superficial gas velocity, liquid velocity, bed expansion, and the settled bed volume to the reactor volume ratio are the important parameters which are to be studied for the for knowing the hydrodynamics of the inverse fluidized bed reactors, the bioreactor. Here for the phase hold ups, in general it was observed that if the, because this phase hold up they important role, play important role to know the effectiveness or to decide the effectiveness of the inverse fluidized bed bioreactor. It is observed that when we are increasing the gas velocity or the increasing the liquid viscosity or the particle density, how the phase hold ups are changing. Here it is observed by the various researchers that this phase hold up, gas phase hold up, phase hold up means fraction of the gas in the bed, that is the gas phase, how much gas is present in the bed. It is observed that this gas phase hold up, sorry, it was epsilon g, it is why it is important, because it is crucial for the transfer of oxygen from the gas or the air to the liquid phase. When because for the growth of the microbes, then as aerobic bioreactor, growth of the microbe, oxygen is required. So, this gas hold up helps or the makes it possible to transfer, to supply the oxygen to the microbes. So, here oxygen level in the liquid phase is essential for the effective growth of the microorganisms, and these researchers have found that this gas phase hold up increases with increasing the gas velocity. It is obvious, if more gas is supplied to the bed, naturally fraction of the gas in the bed also will increase. So, gas hold up it was increased with the increase in the gas velocity, and it was also observed that if you increase the superficial velocity, that has negligible impact on the solid hold up, that is naturally the gas hold up. Gas because if you increase the liquid velocity means more liquid will be there. So, that has no impact on the gas hold up, and here also gas hold up is reported to increase with the increase in the while in the slugging fluidized bed regime. If it is not properly fluidized, slug formation is there, that is layer wise formation is there in the bed, in that case it is this gas hold up may increase with the increasing liquid velocity. Otherwise, in the normal the fluidization regime, the gas hold up is not dependent on the liquid velocity. So, also it is observed that liquid hold up increase slowly from the bed to the freeboard region over a wide transition region. Naturally, if the liquid velocity is increases, the liquid hold up will also liquid hold up, that is fraction of the liquid in the bed will be increasing, and it is observed that in the freeboard region naturally in the bed region more solids will be there. Freeboard means after the fluidization regime, the region is the freeboard region, there more liquid will be there. So, liquid hold up is more in the freeboard regions. So, researchers have worked on the by taking the polyethylene particles or polypropylene particles and they studied the this on the phase hold up, and they found that this liquid phase hold up increases with increasing gas velocity as well as the liquid velocity, whereas at higher liquid velocity this hold ups value remains nearly constant, because they maintain the when the fluidization will be at the, as in the last video we saw that it is already the increasing and it is covering the particles covering the entire length of the column. If you further increase the gas or the liquid, naturally liquid hold up will not increase, it is maintained, steady state we are maintaining. So, further increase in the up to certain level liquid hold up will increase, then after that the liquid hold up will remain constant, because as it is the level of the water in the reactor is maintained, steady state is maintained. So, here liquid hold up decreases with increasing the gas velocity, and liquid hold up also increase with the, it is the normal fluidization regime, but after certain level it is liquid hold up will not change. So, the solid hold up similarly decreased from the bed region to the freeboard region. Naturally, bed region more in the top, as you in the figure we saw, more solids are there in the top region, that is the bed region. So, there solid fraction is more, so solid hold up is more. In the freeboard region towards the lower part of the bed, it is the, that is the freeboard region, there less solids is there. So, solid hold up is less in the freeboard region, and the solid hold up is found to decrease with the increasing gas velocity, means when more gas is supplied, the it is fairly, means what happens, it is the means a thin layer of the solids will be there in the freeboard regions. So, the solid hold up decreases. Similarly, it is observed that solid hold up decrease with increasing the gas velocity, liquid velocity as well as the viscosity of the liquid also. If liquid becomes thick also, solid movement will be hindered, or the getting resistance to move freely into the bottom regions. So, these are the some correlations are proposed by the different researchers who studied on the bed hydrodynamics, that is gas hold up you can see here, all containing the terms, that is gas velocity, liquid velocity, liquid viscosity, and on the liquid phase hold up also. So, it is so considering the that is gas velocity, liquid velocity, density of the gas, liquid, and solid hold up, which is the mass of the solid divided by, here you can see it is the volume of the reactor, means mass of the solid by the density of the solid, that means it is the volume of the solid divided by the volume of the reactor, that is the how much fraction of the solid is there within the reactor. So, solid hold up. So, total sum of the all the hold up should be 1. So, these are the various correlations suggested or developed by the different researchers. Now, minimum fluidization velocity, as already we told, that is also we have to means during the experiments on the minimum fluidization in the using the inverse fluidized bed bioreactor, minimum fluidization velocity for both gas and the liquid has to be determined, because under the minimum fluidization condition only all the particles will be fluidized. Before that it will be partially packed and partially fluidized. So, for which minimum fluidization velocity is to be maintained for the smooth fluidization, or it can be slightly more than the minimum fluidization velocity. And so, different researchers also worked on this and predicted considering the different solid particles, different materials using, and they proposed the correlations for the minimum fluidization velocity also. So, these are the minimum fluidization for the liquid fluidization velocity and for the minimum gas fluidization velocity. So, in terms of the here gas fluidization velocity which was determined in terms of the Reynolds number, viscosity of the gas, Archimedes number. So, different researchers have worked on this. Here also you can see the liquid minimum fluidization velocity, Reynolds number, viscosity of the liquid and some Archimedes number. So, have been used to predict the minimum fluidization velocity. Then hydraulic retention time is also another important parameter for the knowing that how much time is required for degradation of the pollutants from the wastewater. So, it is the hydraulic retention time is calculated, that is T equal to V by Q, volume of the reactor, Q is the wastewater flow rate in the reactor. So, T is the hydraulic retention time, that is how much duration wastewater remained in the reactor for the treatment. So, knowing this we can it is observed that inverse fluidized bed bioreactor, the retention time is less in comparison with the other reactors, because here this aerobic treatment with the low concentration of the and which is easily degrade the low concentration of the pollutants, for which oxygen requirement is less. That is why with the low retention time also degradation becomes that is effectively done. Now, it is observed that percentage of the COD reduction also increases, that is in the inverse fluidized bed reactor with increasing the hydraulic retention for the domestic wastewater and the starch wastewater. It is the some case study, it was for the although the low level of the pollutants can be degraded with less time, low retention time, but it is found that for the COD reductions in comparison to the that is for COD reduction from the domestic wastewater and starch wastewater, slightly higher retention time is required. So, this also depends on the hydrodynamics and the nature of the microorganisms used. What type of the microorganisms we are using, on depending on that we can decide how much retention time to be provided. So, low density plastic biomass support particles, here in the inverse fluidized bed, as in the figure we saw, there that is orange colored polypropylene beads were being used. So, here low density support particles, they provide the surface for the growth of the microorganisms. So, this as they provide the support. So, low density biomass support particles are the also important part in the inverse fluidized bed reactor, because when they grow they attach to this surface, then they take the pollutants from the wastewater as the feed. However, the attachment to the microorganisms also on the solid particles depends on the surface roughness and the degree of hydrophilicity. So, accordingly researchers worked considering the different materials. They observed that if the material is hydrophilic and also surface is rough, then more microorganisms can attach to the surface. And for that some researchers they taking the other materials, that is polyvinyl chloride, they treated the these PVC particles with the solution of the chlorosulfonic acid and also polyethylenine to improve the biofilm formation. So, if you are not taking the hydrophilic material, then or hydrophilic surface, then we have to treat these materials before using in the biofilm reactors. So, the intention is to have the that is hydrophilic nature and the rough surface of the particles, and but usually the spherical particles or the approximately spherical particles are taken, because irregular particles affect the fluidization process, and if you use these irregular particles, then bed stratification may take place. Stratification means layer wise formation may occur. So, to avoid that and to have the uniform growth on the surface of the particles, to have the uniform fluidization, usually spherical particles are taken, or closely spherical particles are taken, such that smooth fluidization will be there and the growth also will be proper in the inverse fluidized bed biofilm reactor. Now, bed aspect ratio also another important factor, and bed aspect ratio, that is h by d, height of the bed to the column diameter. When we are taking the column, diameter is fixed. Suppose we have fabricated one column, diameter is fixed, we cannot change the diameter. Only the bed aspect ratio can be varied. If we bed height, we vary. Bed height means material we can vary, then aspect ratio can be varied. But here with rise in the when we are changing the bed height, that means we are taking more and more particles. As a result, that will require more gas velocity for the fluidization. So, that is why it is observed that with more particles, large number of the solid particles will require more because more surface we are providing, and that means more air flow will also be required. First thing, that is for means for fluidization, when the more materials we are taking, more air will be required. Second thing, more materials means more microbes, microbes getting more surface. So, number will be multiplied frequently, for which they will needing the microbes will be requiring the more oxygen also to grow. So, reactors having low aspect ratio require the low UG, that is gaseous velocity. It is obvious, less material means less air velocity will be able to fluidize the materials. Again, aspect ratio of the, it is observed that by the researchers, that if aspect ratio of the 10 is maintained, then petroleum and brewery wastewater can be treated for the COD reduction up to 64%, and phenolic wastewater, it is observed that degradation rate decreases if the bed aspect ratio is increased above 1.787. That means, it is the optimum level of the bed aspect ratio for the phenolic wastewater. So, that way with the researchers we can, if we want to carry out the experiment or we want to treat the wastewater for the COD reduction, then accordingly we can just getting the information, we can close to that value, we can maintain the bed aspect ratio, such that more effectively COD reduction can be carried out. Now, superficial velocity also another important aspect. So, COD removal is found to increase with increasing the gas velocity. Naturally, more oxygen will be supplied. So, but still if it is not that we go on increasing, then it will be giving more oxygen for the growth, but there is some limit, that is optimal value of the gas supply should be there. After that the COD removal will be decreased. Sometimes more aeration, but there is more oxygen is there, but there is no pollutants in there, or other conditions will be affected, pH will be affected, or the viscosity will be affected, and the fluidization quality, minimum fluidization quality means fluidization will be converted from the smooth to turbulent also, because of which the biofilms which are already formed on the surface of the particles may get damaged also. So, that is why there is some optimal limit. So, beyond that it is decreases. Similarly, gas hold up is found to increase with the gas velocity, while the biodegradation also observed to decrease after the optimal value. So, although up to certain limit there is the means gas hold up or COD reduction increases with the increasing gas velocity, but always there is some limit beyond which it will not it will have the negative impact. So, with increasing the liquid velocity also fluidized bed happen to expand, naturally expansion takes place, but here it is observed initially that liquid hold up increases and solid hold up decreases, bubble size, because solid hold up decreases, that means bubble size will reduce, gas solid interfacial will also be, gas liquid interfacial will increase, and here the minimum fluidization velocity for the gas will be decreasing and volumetric mass transfer coefficient will increase. So, these are the findings of the researchers based on their research works using different materials, different systems. Another important parameter is the Vb by Vr ratio, that is settled bed volume. To the settled bed volume means after fluidization, if you shut off the air supply, then the what is the bed volume, that is the settled bed volume to the reactor volume. So, here reactor volume means entire fluidized bed volume. So, important parameter. So, here for any given mass of the bed Bp subscript is the bed particles, and minimum fluidization velocity for the gas is found to increase with the increase of the Vb by Vr ratio. And for any mass of the bed particles and the superficial velocity, gas hold up is found to increase with the increasing the this Vb by Vr ratio also till the optimal value is reached. And also sometimes it was observed that optimal value of the Vb by Vr decrease with increase of the mass of the solid. Naturally, this aspect ratio Vb by Vr ratio will be changing with the, because settled volume, if we are changing the mass of the bed, naturally volume of the bed also will change. As a result, Vb by Vr ratio will be changing also. So, here COD reduction is found to decrease with rise in the oxygen flow. If more oxygen is supplied, that because this microorganisms may die also because of the turbulent fluidization, as a result COD reduction will also be affected. So, these are the some correlations suggested by the different researchers for the knowing the Reynolds number, minimum fluidization velocity for hydrodynamic studies, where the two phase systems they determine the pressure gradient also. So, these are the few expressions which are suggested for the gas hold up, minimum fluidization velocity, Reynolds number, bubble velocity. So, now we will go to the experimental part for the treatment of the industrial effluent. So, hydrodynamic study helps us to know the conditions of the bed to be maintained to have the smooth fluidization, and with which we can be able to treat the wastewater properly without affecting the life of the microbes. So, here in the inverse fluidized bed reactor, which is was considered as the least important in the past, but now it is gaining importance owing to the various industrial applications, mainly for the wastewater treatment, because it removes the contaminants and the organic material using the less energy and the low cost involvement also. Here several physical, chemical, biological methods are there, as already we discussed. Here it is found that higher efficiency on the removal of the pollutant is observed in the inverse fluidized bed reactors, and other various advantages also is there, as already we discussed in the advantages part. So, it is recommended for the treatment of the wastewater, and here various industrial wastewater case studies are there, and in our lab also we have already studied the some sugar industry wastewater, textile industry wastewater, steel industry wastewater, and some other inorganic such as phosphate sulfate removals also we have studied. And so using these 3-phase inverse fluidized bed bioreactors, we can say that we can successfully treat the industrial wastewater and also municipal wastewaters. Here this 3-phase inverse fluidized bed reactor has inherent advantage over the 2-phase systems due to the improved supply of the oxygen and the elimination of the pre-aeration, because sometimes to supply the oxygen to the microbes, if you are taking the 2-phase systems, so then initially we have to supply some oxygen, aerate the system so that microbes can survive. But here in this 3-phase we will be continuously supplying the air for the aerations also. So steady biomass loading is required, so which is also possible in the inverse fluidized bed reactor easily, and it can be controlled in the inverse fluidized bed bioreactor where the light particles are fluidized to by the downflow of the liquid, because water is supplied from the top. And here we will discuss some phenol, ammoniacal nitrogen, phosphate ion, sulfate ion from the research works which you have already carried out in our lab. Now, chemical oxygen demand, which is calculated, as we know, this is one of the important parameter for the treating the wastewater. So it is an indirect measure of the amount of the organic compounds present in water. It is often used as a rough approximation of the pollution level of concerned wastewater. So we can calculate using this formula A minus B into N into 1000 into 8 by V0. Here A is the ml of the ferrous ammonium sulfate used for the blank one, B is the milliliter of the ferrous ammonium sulfate used for the original sample, and N is the normality of the ferrous ammonium sulfate, and V naught is the ml of the sample, and 8 is taken because it is the atomic weight of the that is nascent oxygen we are taking. So thus COD you can calculate. Similarly, BOD also measures the oxygen which is utilized by microorganisms under the specified experimental conditions during biological oxidation of the organic matter which contained in the liquid waste. So this is the just schematic diagram for the experimental setup which is there in the lab. This is the inverse fluidized bed reactor. Here the you can see that here the through this rotameter, that is the air is supplied and water is supplied from the top, which is again recycled back means collected in a drum, and it is again supplied to the column from the top. Here manometers are connected. If we need to know the measure the pressure drop at a different levels, so different manometers we can connect here also. So it is a perspex column, and these are the bed materials, and here on the top one mesh or screen we can provide to prevent the upward, if you suddenly if you increase the water flow rate, then the particles may carry over, means water may overflow the column. So to prevent that, some screen we may we need to provide on the top of the solid particles here in the or the top layer of the bed. Here just picture of the experimental setup, inverse fluidization. Here the procedure how it is carried out, as two flow is there, liquid flow and the gaseous flow, two rotameters will be there. So that can be calibrated, and then the before taking the experiments or carrying out the wastewater treatment, and the column can be loaded with the solid particles of the required size, and water usually in as per the research it should be within just 2 to 10 centimeter size is taken whatever the data is available in the literature. Here in our lab we have taken 6 size particles. So, water is used in fed from the top and air is supplied from the bottom, and water flow rate is means allowed to attain the steady state by adjusting the inlet and the outlet flow rate, and manometers will be connected. Water flow increases gradually in steps till the bed is completely fluidized. And initially it will be packed bed, as in the figure video also we saw. Initially bed is the packed bed, then partially it is fluidized, then it is smooth fluidization occurs. So, we have to maintain that smooth fluidization corresponding to minimum fluidization velocity. The pressure drop plot also we can from the by plotting the pressure drop versus velocity, we can get the minimum fluidization velocity also. And here then once the minimum fluidization is attained or the smooth fluidization is attained in the bed, we can introduce the cultured microbe which is separately cultured inside the column and allow the microbes to grow within the column under the steady state conditions and the minimum fluidization conditions. Then after few weeks, when it will be the microbes will be 2 to 3 weeks time, we can collect the samples, so that microbes will be grown, and then we can verify that whether the films have been formed or not using the technology. Here usually in our research that is work, the students had used the eSEM to measure the biofilm formation, thickness of the biofilm formation, and that again indirectly also concentration of the sample wastewater which is there in the column can be collected from time to time at regular intervals, 6 hours, 10 hours intervals, and to check that whether what is the level of the pollutants in the sample, so that we can know that it is getting the pollutant level is getting degraded gradually or not. Now, for the phenol degradation, the inoculum was activated sludge was the activated sludge taken from the biological unit of the steel plant, local steel industry, and there some it was wastewater was enriched with the mineral salt. Then the that is taking the it is cultured, and then it was introduced in the inverse fluidized bed reactor. Similarly, for the sugar industry also, the inoculums were collected from the sludge taken from the starch industry, and inoculums was also introduced, and another was some experiment, I do not remember exactly. We had collected the wastewater for that inoculum was the wastewater of the dairy, that is unfed wastewater we had collected to prepare this, to culture this microbes also. So, then here if the difference in the weight of the biomass in the reactor at 2 consecutive samplings differs only within 5%, it is considered as constant biomass growth. If that is suppose 6 hours interval we are collecting the samples, we can check that what is the that is weight of the biomass. So, what was the biomass in the first sample, and what is the biomass in the second sample. If there is the 5% difference, that means growth of the biomass is there. So, we can ensure that biomass being grown in the reactors. So, biomass slugged up from the particles can and separated from the effluent in removed from the system to determine the COD reduction experimentally as per the equation. COD or the whatever the pollutants will be there. So, just this is the general procedure, whatever may be the pollutant, this is general procedure. Now, it is for the this the data for the phenol degradation. We had I have taken that research paper, one of the research paper which used the steel industry wastewater for degradation of the phenol. The growth kinetics, it is the growth kinetics. It is the comparison of the COD removal. COD removal was found out with and without addition of mineral salt treatment, that is during the culturing. So, 3 ways it was cultured, that is the without the salt addition and with the salt addition, again wastewater plus mineral, here wastewater plus double amount of the mineral, means increasing the amount of the mineral also. So, here it is compared, and we can see that when double amount of mineral is added, that is green color, it is the COD removal degradation is more. Here the correlation was developed for the COD removal against the system parameters, where the parameters were bed height, where bed height was varied, flow rate of the gas, flow rate of the water, then the retention time, time of the that is how much time the it was allowed to grow, then the VB by VR ratio. With this correlation was developed. This is the correlation. So, it was found that pH level for the steel industry effluent after the microbial treatment is reduces from the 7.3 to 8.6, which are near to neutral range of the pH of water. Highly efficient performance of the inverse fluidized bed bioreactor stems from the high biomass connection, which is enhanced or which is achieved due to the immobilization of the cells onto or into the solid particles. Now, it is found that also after 3 weeks, means because biomass loading practically constant for the period of 3 weeks. After 3 weeks, it is visible that is the biomass growth is there, means by seeing that solid particle also we can see, and the bioreactor performance is satisfactory, and that is with approximately 70% COD removal, and good performance of the bioreactor was achieved. So, this equipment well suited for the treatment of the industrial wastewater, including samples containing phenols. So, COD removal was found to be 84% with the continuous culturing mode, and therefore, inverse fluidized bed can be used as an effective bioreactor to treat all types of the industrial effluents biologically. This was the conclusion for that research paper, where the Tanmay Limma and myself were published. Tanmay Limma, one of the MTech student, were there. Then phosphate ion also. Here for the phosphate ion, it was also same inoculum was used from the biological that unit from the steel plant industry. We are collected the sludge from there. With that we that is microbes were cultured, and here it was phosphate sources. If you see, wastewater stems from the household streams from the household and the industries contain significant amount of the phosphates. Major source of phosphates in these streams are human excreta, widespread usage of detergents, cleaning agents, and laundry services, and waste containing food and eatable as well. So, besides these sources, industries which deal with wide variety of chemicals also discharge phosphate enriched wastewater. So, our municipal water contains municipality water contains lot of phosphates, because we are that detergents and the here the cleaning agents were being used, and that is drained out, that is also containing lot of, because of that lot of phosphate ions are present. And also sometimes water runoff from the agricultural lands using the fertilizers majorly leads to the phosphates entering the wastewater stream also. These phosphates are mostly present in the two forms, dissolved form or the particulate form, and dissolved form mostly in the orthophosphate form, and some of the phosphates are also present in the polyphosphate form. So, excessive discharge of this phosphate into the water bodies leads to eutrophications. So, here thus because of this what happens, there will be uncontrolled growth of algae and cyanobacteria, which will block the sunlight from reaching the lower levels of the water, and causing the plants to die. When the plants will be dying because of the growth of this algae, the uncontrolled growth of algae and cyanobacteria. So, there is also some reduce the oxygen content of the water level, and also the it will cause the death of when the oxygen content of the water will reduces. So, naturally aquatic life will be affected, and thus algal blooms resulting from this phosphate concentration will be toxic and makes the water body also unfit for the utilization. So, here this was the growth kinetics for the microorganisms which was used for the phosphate reductions. So, this was the ESM plot which ensured that there is the film formations on the surface of the particles, and variation in the phosphate reductions concentration. So, a sample plot, because it was 10-12 experiments were there. So, it is found that concentration of the phosphate is gradually decreasing with the time. So, this is also for the different initial concentrations it was compared, all with the all initial concentration phosphate reduction is found to decrease also. Now, you can say removal of the phosphate wastewater. So, here similarly conclusions, here also we can same conclusions. It is as phosphate reduction is possible. So, it can be used as a bioreactor for the treatment of the wastewater. Similarly, for the you can see for the sulfate ions, you can see here sulfate ions, here the growth kinetics, here also is same plot, and you can see with the time how the concentration is reducing. Here you can see initial sulfate concentration, fine sulfate concentration of water. Here you can see variation in the for the different initial concentrations are with the sulfate ion decreasing, and here the air flow rate, and here the pH how it is affected, pH is changing. So, this is again another example for the ammoniacal nitrogen. Here also we can see the that hydrodynamics, we can see solid hold up versus UG, and this is the solid hold up for the VB by VR ratio. This is the liquid hold up for the gas velocity, and you can see growth kinetics for the microbes. Here the ESM analysis. Thus, here also it is found to how ammoniacal nitrogen concentration is reducing with the time. So, it is for the 3 different initial concentrations you can see, and this is the efficiency, how you can see how the efficiency with the time also changing, that is ammoniacal nitrogen reduction is changing, means increasing with the time also. So, thus we can conclude that inverse fluidized bed bioreactor can be operated continuously as under semi batch mode as a stable performance which gives stable performance for the 27 days. So, we can conclude that it is most suitable bioreactor for the treatment of the industrial wastewater. So, thank you. Any questions? Okay, if no questions, we stop here. Okay, thank you. ଅଧ ଘଣ୍ଟା ତ କହୁଥିଲି।
next channel. Pipit down kore. Haba. Ei window tadi. Iya udah. Last টা।
जो चारटे के बॉक्स है हाँ सेट शेयर स्क्रीन पर
I can, huh? Share screen. Good afternoon to all. So in continuation to my previous lecture on hydrodynamics of gas liquid solid three phase fluidized bed, where I had talked up to the experimental hydrodynamics study. The rest part of that talk was the computational hydrodynamics study, which is named as a CFD simulation of a gas liquid solid fluidized bed. So CFD means it is the computational fluid dynamics. Using the computational tool, the fluid dynamics problems are solved in this approach. In engineering, generally to solve the problems or to develop new systems, design a system, there are three approaches. One is the experimental approach, where the actual system we first based on our knowledge we fabricate it, then perform experiment on that, and using the experimental results again we can modify. If we are not achieving our expected thing, then we can modify the system. That is the approach, that is experimental approach. So a lot of time is required in this experimental approach, time consuming, and resource is also required to develop the setup. But another approach is the computational approach. If somebody is good in mathematics and knows the physics of the situation very well, then can develop mathematical model. And the mathematical models are of different types. The mathematical models may be algebraic equations, mathematical algebraic equations are there, ordinary differential equations or partial differential equations are there. Depending upon the number of equations and the type of differential equations, the complexity in solving the equations comes. And so good mathematical solution techniques if we have, then complex model we can develop. The advantage of this mathematical modeling is that microscale phenomena can be observed and analyzed in the mathematical model. A third approach in between the purely experimental and the mathematical one is the scale up models like the dimensional analysis. So in the dimensional analysis, what we do, a small scale model, we perform the experiment, and a number of experiments required here comparatively less, and in the form of dimensionless numbers we come out with a certain equations to explain the parameters dependency on different operating variables, and which are easy to scale up. That means a large scale actual prototype can be developed from this small scale model equation. So purely mathematical model, it is good that they complete the physics of the situation, the microscale phenomena can be analyzed well, so that computational fluid dynamics is one such thing, and there are various computational fluid dynamics tools available in solving the things. In the absence of that, we can write, if we are good, we can write the set of mathematical equations starting from mass balance, energy balance, your momentum balance, then transport equations, reactions, thermodynamic equations, everything. We can write those equations and we can solve those. And when we are having the ordinary differential equations, the solution technique is easy, like numerical techniques, Runge-Kutta fourth order, any other technique we can apply to solve those equations. But when it comes to partial differential equations and with many variables, then it is very difficult to solve. That's why the techniques are there. We discretize the entire system into small volumes, those are called the control volumes, and using those control volumes, these the differential equations are discretized to a large number of algebraic equations, and using the algebraic set of algebraic equation solution technique, those things can be solved, and we are getting the information on each of the cell or the grid for the in the computational domain, and which are then one cell to other cell, the information flow is there, and overall for the entire computational domain we get the information. So as far as the computational fluid dynamics is concerned, as I told, it is a powerful tool for the prediction of fluid dynamics in various types of systems, thus enabling a proper design of such systems. One of the CFD technique is the finite volume method, which is the most versatile discretization technique used for solving the governing equations for fluid flow, heat transfer, and mass transfer operations. So the advances in physical models, numerical analysis, and computational power enable the simulation of multi-phase flow characteristics in 2 or 3 dimensional circumstances, whether it is for mass transfer, heat transfer, or species transport or momentum transport. Computational fluid dynamics has emerged a new paradigm for modeling the multi-phase flow and the fluidization. And here the finite volume method is in the finite volume method, the solution is exactly satisfied for any control volume as well as for a whole computation domain. Even a coarse grid solution exhibits exact integral balances. It can be applied to any types of grids, whether it is a structured grid, unstructured grid, Cartesian, or body fitted type, and especially to complex geometries. In the finite volume method, the solution domain is subdivided into continuous cells or control volumes, where the variable of interest is located at the centroid of the control volume, forming a grid. The next step is to integrate the differential form of the governing equation over each control volume, and interpolation profiles are then assumed in order to describe the variation of the concerned variables between the cell centroids. There are several schemes that can be used for the discretization of governing equations. Example, central differentiating, upwind differentiating, power law differentiating and quadratic upwind differentiating schemes. The resulting equation is called discretized equation. In this manner, the discretization equation expresses the conservation principle for the variable inside the control volume. These variables form a set of algebraic equations which are solved simultaneously using special algorithms. So, in this present discussion, I am going to discuss the CFD simulation of a gas liquid solid fluidized bed. A two-dimensional transient model has been developed to simulate the local hydrodynamics of gas liquid solid three-phase fluidized bed here. The hydrodynamic behavior studied numerically is the bed pressure drop, minimum fluidization velocity, bed expansion or bed voidage, and phase hold-ups, and validated with the experimental results. This slide shows the hierarchy of the multi-phase models used. The model type empirical, as I already have told, ideal flow patterns, phenomenological models, volume average conservation laws, point-wise conservation laws. As you see, the empirical model is straightforward. You have carried out an experiment, and a parameter you are expressing in terms of the operating variables. And so, if you have the values of the variables, you can easily calculate the value of the parameter easily. So, it is a straightforward model, but it never gives the deeper insight into the phenomena that is happening in the system. As we go down, okay, the point-wise conservation law, if we use, which is very difficult, even if sometimes it is impossible to solve also, because we do not have the solution techniques with us. But the thing is that a significant insight or microscale phenomena, okay, can be explained using this point-wise conservation laws. So, what this finite volume method application in this computational fluid dynamics that I am going to discuss is nothing but the volume average conservation laws, okay, that is used here. So, to simulate the gas liquid solid fluidized bed, as it is a cylindrical bed, so it is axis symmetric. For that, even if I am taking the two-dimensional model of it, nothing wrong. I can get all sort of information, hydrodynamic information which is needed from the two-dimensional model also. A three-dimensional model can be done, but it will be computationally intensive. Large time will be required for the computation. Huge computation, computing power is required. So, then for that computational model, the certain model equations are written, and those model equations are solved. So, in this particular case, an Eulerian granular multiphase model, many types of models are possible. The one model which is chosen is the Eulerian granular multiphase model is adopted, where gas, liquid and solid phases are treated as a continua. That is, an Eulerian treatment is used for each phase, and it is interpenetrating and interacting. The phases are interpenetrating and interacting with each other everywhere in the computational domain. That is the assumption. And the pressure field is assumed to be shared by all the phases in proportion to their volume fraction. So, the conservation first step is the conservation equations. As we are going to study the hydrodynamics, so the equations are continuity equation and momentum equations. Energy equation is not required, heat transfer we are not going to evaluate heat transfer characteristic. So the first one is the conservation equation of the mass. This is the continuity equation. One is the transient term, then the divergence of this quantity. This is the conservation equation, where epsilon k is nothing but the phase fraction. The k can be solid, liquid and gas separately, and this rho k is nothing but the density of the phase. It can be rho s, rho l and rho g. Similarly, the uk here is nothing but the velocity of that phase, solid phase, liquid phase or gaseous phase. Then sum of the phase fractions in this system is equal to 1, epsilon L plus epsilon G plus epsilon S. Now next the momentum equations. There are different momentum equations for the liquid phase, gas phase and solid phase. As you see, the left side what you get is nothing but your this that is the force of inertia, you can say, and first is the this term is your transient term, second is the convective acceleration, that term, and the right side the sum of the forces, this pressure force, that shear force, and the body force or the external force. So it is the Navier-Stokes equations. It is written for the liquid phase. As you see in the liquid phase, gaseous phase and the solid phase, mostly the equations are similar, but in the solid phase one additional term is there. So in these equations, your P is nothing but the pressure shared by all phases, and your the second term here, the additional solid pressure in the solid phase, that momentum equation, another term is there, where is nothing but the additional solid pressure due to the solid collision, and then the this term FIL, FIG and FIS, these terms are nothing but interphase momentum exchange terms are there. So these are interphase momentum exchange for the liquid phase, gas phase and the solid phase. And this is tau L, tau S, tau G, these are nothing but the stress tensor for liquid, gas and solid phase. And mu L, mu G, mu S are the shear viscosity. Here mu is the shear viscosity. Sorry, next. Yeah. So this tau L is nothing but tau L, tau G, tau S are the stress stress ବନ୍ଦ ନାହିଁ କେତେ ଗୋଟେ ବନ୍ଦ ହେଇଛି ଚେକ୍ କରିଥାନ୍ତ ନା ଚାଲିଥିଲା କେତେବେଳଠୁ ବନ୍ଦ ହେଇଛି so this gamma theta s is nothing but the energy exchange the collision dissipation energy represents the rate of energy dissipation within the solids phase due to collision between the particles. This term is represented by the expression derived by Lone and co-workers and which is given by this. These are all empirical relations. Then this phi ks is nothing but the energy exchange between the kth fluid phase and the solid phase is represented by this equation, so that the solid stress tensor is given by this, which is nothing but the term for collision, kinetic energy and friction is there. So this solid stress tensor contains shear bulk viscosities arising from the particle momentum exchange due to translation and collision. The solid shear viscosity contains collision, kinetic and frictional components of viscosity, whereas this shear component is expressed by this equation, kinetic component is expressed by this equation and the friction component is expressed by the third equation here, where Ps is the solid's pressure and phi is the angle of internal friction, and this I2d is there, which is nothing but here denominator of this is the second invariant of the deviatoric stress tensor. There are two types of stress tensors we know. One is the because of the change of the volume, another is the change of the shape. So deviatoric stress tensor is because of the change in the shape that we get. Next, closure laws for the turbulence. To describe the effect of turbulence fluctuations of velocity and scalar quantities, the simplest but complete model is the two equation standard K epsilon model, as we know. Turbulence is a very complex phenomena. As per fluid mechanics, there are two unanswerable things in this world. One is turbulence, another is uncertainty. According to fluid mechanics, God can answer the uncertainty but not the turbulence, because it is so complex and chaotic in nature. So a very straightforward expression to explain the turbulence, till now it is not there, but approximations are there. So K epsilon model is one of the suitable model. The number of terms to be modeled in the momentum equations in the multiphase flows is quite large, because three phases, so interaction between them, and this makes the modeling of the turbulence in the multiphase simulations extremely complex. There are three methods for modeling the turbulence in the multiphase flows within the context of K epsilon model. Those are the mixture turbulence model, number one the mixture turbulence model, second the dispersed turbulence model, and a third type is the turbulence model for each phase. So as in this present situation, we have a continuous liquid phase and the dispersed gas and the solid phases. So the K epsilon dispersed turbulence model is considered here for the turbulence modeling, as this model is applicable when there is clearly a primary continuous phase. So already liquid is the continuous phase. So using the K epsilon dispersed turbulence model, the turbulence in the continuous phase is calculated using the equations, and the ED viscosity model is used to calculate the average fluctuating quantities, where in the ED viscosity model the Reynolds stress tensor is expressed for the continuous phase. It is expressed by this equation, and in this expression you see the terms, the turbulent viscosity, the turbulent viscosity is written in terms of turbulent kinetic energy. This is the turbulent kinetic energy, KL is there, and a characteristic time and a energetic turbulent eddies are defined by, this is your one is the this is the time, and this is the length scale of the eddies, and this is the time. So that here epsilon L here used is a different, it is not the phase fraction, rather it is the dissipation rate. The epsilon L is the dissipation rate, and C mu is nothing but, everywhere it is that C mu is used. C mu, it has a value of 0.09. This is a constant parameter. So the length scale of the turbulent eddies, as I have told, is given by this, whereas the time is by this equation. The values of this KL and epsilon are directly obtained from the differential transport equations for the turbulent kinetic energy. KL is the turbulent kinetic energy, and sigma L is the turbulence dissipation rate. So these are obtained from the differential transport equations. The equations are similar to the Navier-Stokes equations. The turbulent kinetic energy, this equation is used, and the turbulence dissipation rate, this other equation is used. Then there are turbulence, as it is a very complex phenomena, so large number of model equations are there successively we have to. So because of shortage of this time, I am not discussing those in detail, rather the So next is the numerical solution to these equations, which is the numerical methodology. So the model equations described above are solved using commercial CFD software ANSYS Fluent. The fluidized bed reactor considered for the present simulation study is a cylindrical column of a diameter 0.1 meter and height of 1.88 meter. The governing equations as we have discussed are discretized using element based finite volume method, and for spatial discretization of the governing equations, high resolution discretization schemes are used, which accounts for the accuracy and stability. For the time discretization of the governing equations, a second order backward Euler scheme is used. The discretization equations are solved using advanced algebraic multi-grid solver technology. So in the numerical methodology, one is the geometry in the commercial CFD software, and then basing, that means dividing that into finer control volumes. So as I have told, it is a geometry is made using the design modeler of the ANSYS Fluent. Okay, the diameter is 0.1 meter and the height is 1.88 meter. It is taken. After the geometric creation, a uniform mesh has been generated with a map structured quadrilateral elements. So quadrilateral meshing is done containing height to width ratio of 1, and the mesh 2D mesh is shown here. Then the flow chart for showing the general procedure for the simulation of the ANSYS Fluent is this: set the solution parameters, initialize the solution in the numerical methodology only, then enable the solution monitors of interest, calculate the solution, and the calculated solution, from the calculated solution we check the convergence. If the convergence is there, then if it is yes, then we go for the check of accuracy of the result. If it is yes, then we stop. If it is no, at this convergence, if convergence is not there, then we modify the solution parameters or the grid. And if convergence is there but accuracy is not there, again we go back and modify the solution parameters or the grid. That means then again we recalculate that. So this is the procedure. So the mesh, as you see here, a 2D mesh and a 3D mesh is shown. So cell or the control volume, as I have told, for 2D mesh it is the cell, for 3D mesh it is a 3-dimensional cell. Okay, then face, edge, node, cell center, etc. These are the things. So this is the meshing. Such meshing is done for a 2D geometry. So totally 7,520 cells with a size of 0.005 meter by 0.005 meter have been used for the computation. As already I have told, Eulerian granular multiphase model has been solved to simulate the flow behavior using commercial CFD package ANSYS Fluent. The two equation K epsilon dispersed turbulence model is used for the turbulence modeling. Phase coupled simple method is chosen for pressure velocity coupling. GIAN drag model is used for the liquid solid and gas solid interface drag force calculation, which already we have discussed those model equations. Scalar-Newman model is used for the gas liquid interface drag force modeling. The governing equations are discretized using element based finite volume method in Fluent. So to have the solution of the set of equations, we need the initial and boundary conditions. The inlet boundary conditions is a uniform flow of the liquid and a gas velocity. That means uniform liquid velocity and the gas velocity at the inlet to the bed, and the outlet boundary condition is the pressure boundary condition, that means atmosphere pressure at the top. So the wall boundary conditions are no slip boundary conditions for the liquid phase, and it is the free slip boundary condition for the solid phase and the gas phase. So in this table, the detail of the parameters used in the simulation are given, where the initial bed porosity is considered as 0.41, that means the solid volume fraction in the static bed as a 0.59 is taken. Second order upwind scheme is used for the discretization of momentum, turbulence kinetic energy, and the turbulence dissipation rate. You see that similar Navier-Stokes equation we had for the momentum equations, whether for solid phase, liquid phase, or gaseous phase. Again we had it for the turbulence kinetic energy and a turbulence dissipation rate. So the first order upwind scheme has been used for the discretization of volume fraction equations, and the time step size of 0.001 second is used here. The convergence criteria for all the numerical simulations are based on monitoring the mass flow residual, and the value is 1 into 10 to the power minus 4. That means 0.0001 is set as the convergence criteria. If between the two values, if that is the difference, then that is acceptable and we can stop. That means convergence is achieved. The under relaxation factors used for different flow quantities. For pressure it is 0.3, density 1, body forces 1, momentum 0.2, volume fraction 0.5, granular temperature 0.2, turbulent kinetic energy 0.8, turbulent dissipation rate 0.8, and turbulent viscosity 1. The simulations are carried out till the system reaches the quasi steady state. Quasi steady state means the thing, because it is a dynamic system with the flow of the gas and the liquid, the fluidization is there, particles rise, particles fall, okay, continuous motion of the particles, gas, liquid is there. So it is not a purely steady state, rather it is a quasi steady state. So what is then the solution of this is monitored by the residual plot. Okay, this shows the residual plot for the progress of the simulation. So as you see, in the residual, continuity is solved, velocity of water, velocity of air, velocity of gas, which we get from the momentum equation. Then x component velocity, then y component, that velocity of water, air, and this glass means this is the glass bits are used here. So that's why the name is coming glass. Then k and this epsilon values, and this friction velocity for air and for the glass. These are the residuals are monitored for that. As you see, that convergence is achieving. This is 0.001. So convergence is achieved, but the simulation only in the 70 iterations almost the simulation is converging. So now the quasi steady state, as I have told you, as you see, with the time of simulation up to 30 seconds the simulation is shown. This is the physical time of simulation, but in the system computer, okay, it might have taken days. Actually it has taken more than 1 day for the simulation, but as per the time step size is 0.001 second is taken. So with that the value is coming 30 seconds. So you see that initial static bed height, then for the same inlet velocity of the liquid and the gas, gradually with time as the simulation progress, the bed height is increasing and the liquid gas jets are forming like this. Then gradually it is coming. You see the last three things, 18 second, 20 second and 30 second, up to 30 second. There is hardly any difference. So it is a quasi steady state is reached. That means we have reached at the solution or convergence is there completely. So till that the simulation can be continued, but instead of 30 seconds, the simulation is continued for 60 seconds of the physical time. That means more than 2 days. And the results, next the results are shown here. The contours of volume fraction of solid, liquid and gas in the 3-phase fluidized bed. So this is for solid, liquid and for the gas phase. Solid volume fraction, you see for this particular velocity the bed has expanded. Initially the solid fraction was nearly 60%, 0.59 it was. Now you see the maximum value, if it is red also, you are getting only 20%. That means bed has expanded to a greater height. Initially the bed height was like this only. Okay, now the bed expanded. So solid volume fraction has decreased. Then your liquid volume fraction, as it is a continuous phase, it is the highest here, nearly 80% the liquid volume fraction is there, and gas volume fraction is poor, 2 to 3% gas volume fraction. From this color you can see here 2 to 3% maybe there, 2 to 3% here. Then this is the velocity vector plot, that is the contour plot. This is the velocity vector plot for the solid phase, liquid phase and gas phase, how the solid velocity, liquid velocity and gas phase velocity is changing. Here you see up to this that bed is fluidized with the solid particles. You see that not in a particular direction this velocity vectors are there, rather the fluidizing actually particles are moving in a circulating manner up to this. Above that, okay, so above that there is a in this lower region it is like this. Above that you see in the centrally little bit that rise of the particles are there, then they are falling. Okay, both types of arrows are there, upward arrows are there and downward arrows are. So then the solids are falling again. So that is they are in the fluidization which we are getting from the simulation. As far as the liquid phase is concerned, you see that liquid, all the vectors are in the upward direction. In the central zone you see that the velocity is a little more here in the central zone, but the velocity is less towards the wall. From the XY plot again we will discuss the same thing, that the velocity profile, how it is there in the bed for the liquid phase. For the gaseous phase again it is the same thing, the central zone little higher gas velocity is there, and the gas velocity is more in the freeboard region, that means above the particles. Bed is fluidized up to this. Here you see the magnitude of the gas velocity is less. Already in the experimental analysis for the hydrodynamics of gas, liquid, solid fluidized bed, already we have discussed that phase hold up. Phase hold up is not based on the inventory. Inventory means suppose 2 liter per second the liquid is flowing and 1 liter per second the gas is flowing. So that means gas volume fraction should be, as per inventory, it should be 33%, but it is not so in the bed because these are non-ideal systems. So that's why the study on the gas hold up is there. You see here it is different. In the fluidized bed it is different. Gas velocity is less, as you see, but the gas velocity above the bed, that means up to which the particles are there, gas velocity is less. Gas velocity means gas is moving in the form of bubbles. So bubble velocity is less, and above that in the two-phase region, that is with the liquid only, this portion that liquid and gas only is there, the bubble rise velocity is more. That means bubbles fast escape. As the bubble fast escape here, definitely the gas hold up will be less here, and here the gas hold up will be more because of the larger residence time of the gas in the fluidized bed. So this is the XY plot of the velocity magnitude of the liquid phase and the magnitude of air. You see the parabolic velocity profile almost you are getting like this in the fluidized bed. So the parameters of importance in this gas hydrodynamics of the gas liquid solid fluidization, what we have considered is the bed expansion or bed voidage, your pressure drop and the phase hold ups. So the bed expansion, as you see, with increase in the fluid velocity, you see that fluid velocity is 0.035 meter per second for the water velocity. There is no fluidization, it is almost the static bed is there. As we increase the fluid velocity like this, so the bed starts to expand here, from here. The minimum fluidization velocity is reached. After that, okay, the expanded bed we are getting. And for a fluid velocity of 0.12 meter per second, you see that bed expansion is up to this. This is the expanded bed height. As the bed expansion is more and more, bed voidage will be also will be more. Void means empty space. That means the space occupied by the liquid and the gas. Solid fraction will decrease. So void fraction means or bed voidage means 1 minus epsilon s, that is the solid fraction. Solid fraction will decrease. Up to this, bed height is considered up to this, up to which the solids are there. Okay, so solid fraction is decreasing and bed porosity is increasing. And how the height of the bed is measured? From the XY plot, the volume fraction of the glass means glass beads are used, that is the solid particles. So here see up to this that glass beads are there. Up to this height, above that the solids are 0. Okay, that is the free body region where only gas and liquid is there. So from the simulation, again the bed height versus the superficial liquid velocity at different gas velocities, again it is plotted and it is similar to that of the experimental finding we have got. Now next the figure in the right shows a comparison of the simulated result and the experimental results for the same condition, almost a close agreement. Everything is almost matching with. That means the model which we have developed and solved and the appropriate solution technique has been adopted. Because of that, it is giving the result which is coinciding with that of the experimental observation. Next, the bed pressure drop, as you know, so bed pressure drop is the representation of the drag that is required to make the solid fluidite. But again, in a three-phase system, it is the bed pressure drop is the combination of the drag force, the phase hold-ups. So more amount of gas will be there means the bottom the pressure will be less. Simply liquid solid system, the pressure will be more for the same amount of fluidization as the bottom of the bed. But when gas will be there, for gas fraction, okay, the mass of the gas is negligible, so that the pressure which will be observed at the bottom will be less. So as you see that bottom, the red color is there, so the pressure is maximum at the bottom. As you go above, the pressure decreases. That is as usual thing. Okay, it is the hydrostatic pressure. So with the rise in the height, that pressure will decrease. Then the variation of pressure drop with liquid velocity at a different gas velocities are plotted here. This is the case of this zero, not zero, it is very low. Oh, there is something wrong here actually in writing actually here. So it is the lowest velocity. So lowest velocity, gas velocity, you see the bed pressure drop, okay, observed from the simulation is also high. As I have told that with increase in gas velocity, gas hold up increases. So with increase in gas hold up, the bed pressure drop variation is like this. Then the variation of bed pressure drop for with the gas velocity, which is represented like this. Then a comparison of the bed pressure drop for the simulated result and the experimental results. You see that they agree very well, close agreement between the simulation and the experimental results are there. The next is the phase hold up. So one of the phase hold up, that is the gas hold up, is considered here. The volume fraction of the air. As I had told you that three-phase region and two-phase region, from the vector plot you have already seen. You see that the phase volume fraction of air in the three phase region is more, and in the two phase region it is less because of the bubble velocity. So bubble velocity is more in the two phase region, bubble velocity is less in the three phase region because of the back mixing of the solids. And the variation of the gas hold-up with liquid velocity at the different gas velocities are plotted here. This is the simulation which is similar to that of the experimental results. Again, it is the variation in the other way it is represented. Now this right side plot shows a comparison of the gas hold-up, the experimental measured one, and from the simulation what we have got. Okay, there is a very good agreement up to a superficial velocity of 0.1 meter per second, but after that they deviate little. That means the model which we are using for the gas hold-up in the computational, that models what we are using of the mathematical equations which we are using, that is not explaining the real situation. Okay, modification of that is required for this in this region. Okay, this is all about the CFD simulation of gas liquid solid fluidized bed. Thank you all. If you have questions, please ask. If no questions, then I stop here. Thank you.
Everybody, I'm Mitali Gowda. I'm going to start the experiment of inverse fluidization bed. Now, this is the column, inverse fluidization column, which is shown to you earlier, and here is the distributor. Like ma'am told you earlier that there is a screen which protects the solid particles to move out from the perpex column. This is the perpex column, this is the mesh, this is the distributor, air distributor, this is the counter current flow reactor. So air will flow from downward to upward direction and water will flow from upward to downward direction. The main difference is fluidized bed reactor and inverse fluidized bed reactor is the particle density. We are using a lighter density particle here, so that when we will fill the water in the perpex column, the particles will move upward using the buoyancy force. Then when the water will be filled into this perpex column, we will first measure its static height. When there will be no water is flowing inside the column, we will maintain the height of the particle, and we will record the static bed height HS. Then when we will again attain a steady state by controlling the inlet and outlet valve of the water flow rate, so that it will maintain a constant height. Then we will supply the air so that bubbling will happen. When bubbling will happen in this way, particle will get fluidized and it expand in downward direction. The highest expansion will be H max, the height which we will record, and the lowest expansion will be the H minimum, the minimum height the packed bed will expand. Now I am going to show you how the working is done in manner. First, valve is open. Now we will close it and sorry, I have not. Pump, you can see bubbling is taking place and water is flowing. Close the valve. Close it. पूरा close कर दो. हाँ ठीक अच्छे सेटा स्टैटिक बेड हाइट नबा पे देखो छे. रुहो तमे किसी से पूछो. That's the lower density polypropylene balls of size 6 mm diameter and 870 kg per meter cube densities. Now, as we have filled water in the perplex column, now we can measure the static height, which is 35 minus 12, which is 23 centimeter. Now we will switch on the water flow rate and we will calculate. We will see the flow rate here. This is the flow meter. Digital flow meter. We will see the water flow rate here, and then we will attain a steady state by controlling this outlet valve and this inlet valve. Open. And pressure drop, and we have connected it with here in the column where water up to which height the water is fixed. We have fixed it here, one here, and one end of the manometer here, so that we will calculate the pressure drop of the whole column. Then start. Now to attain the steady state of the flow inside the and Also outlet the water so that it maintain a steady state height. Point 1 flow rate nahi 0 अछि अटी करो. टेन अब दिव्यांशु देखी ठीक अछि. We will write serial number, rotometer reading, H minimum, H max, H static height, manometer height 1, manometer height 2, and R and small r. This R and small r nothing but dimensionless number. R is equal to H max plus H minimum by 2 by H static height. R is a dimensionless number which indicates the greater expansion, suggesting the fluidization and mixing. It helps in determining the optimal operation parameters like fluid velocity. When R will be greater than 1, we will say that it is well fluidized, and when R is similar to 1, we will say that it is not a good fluidized or not fluidizing properly. R depends on the particle size and density and the fluid velocity. And small r is the ratio of H max to H minimum, which says the bed stability. When at higher R value, stability decreases as excessive expansion is there and particle entrainment will happen. At lower R value, we can see poor fluidization and insufficient particle suspension. So for R greater than 1, proper expansion of the bed will happen where the particles are fluidized and suspended in the liquid flow. टिके कमाओ दिव्यांशु, टिके कमाओ. Position we have attained the steady state, and from here we can see the water flow rate, that is 0.5, and we will write it here in the table. And now we will pass on the air. Error of 0.5 only. Now from this compressed column, no, constant bubbling, continuous, man. से खोला स्लो बबलिंग हो किंतु टिके स्लो. This is not working actually. This is from that one. Bubbling is the air flow rate is high, with a high velocity air is flowing inside. Therefore vigorous fluidization is taking place. Fluidization here. That's why if we will pour water and we will pass air, it will burst out from the top, which has happened earlier also. from the calculation we have stated that the air flow rate is at 18.9 meter cube per hour, and the H max का कहते थे 67.21. H max is 67 minus 21, that is 46 centimeter, and H minimum we will calculate. Minus 33, that is 24 centimeter, and static bed height which was calculated earlier is 23 centimeter. Manometer reading from this value we will calculate the R and R. R is equal to H max, which is 46 plus 24 by 2 by 23, and small r is equal to 46 by 24. Solid hold up is nothing but the ratio of solid volume to the bed volume. Solid volume we will calculate by as solid volume is equal to 800 by 870, which earlier it was calculated 800 gram. The total bed weight is 800 gram, the polypropylene ball, and its density is 870 kg per meter cube. So by this we will calculate the solid volume, and by the bed volume as by 2 pi RL, by pi R square L, we will calculate the volume of the perpex column, the bed column. So and by this we will ratio it and calculate the solid hold up. And now coming to the static condition. In static condition, pressure drop is equal to A static into particle density minus density of fluid into gravitational force. Density of fluid is this. Now, in the manometric fluid, in the manometer we have poured carbon tetrachloride whose density is 1.5867 into 10 to the power cube kg per meter cube. And when we increase in static condition, when we increase the fluid velocity, pressure drop also increases, reaching a maximum, which shows us the minimum fluidization velocity UMF. At this point, the drag force exerted by the fluid balances the weight of the particles. In the fully fluidized state, fluidization is achieved and delta P stabilization and become relatively constant. Beyond the fluidization, very high fluidization will occur and pressure drop will decrease. Now, after calculating from this table, first we will make this table in which water flow rate will be constant, and we will vary the air flow rate to take the hydrodynamic study, and then we will constant the air flow rate and take the water flow and vary the water flow rate. After that we will vary the packed bed height. Now the static bed height is 23 centimeter. We will remove some of the particles and maintain some height. So and by that we will make this third column, and after that we will plot a graph between delta p and u. Here in this graph, first when we increase the velocity of the air, the pressure drop increases steadily, and after increasing and this is called the UMF, minimum fluidization velocity, and after that we can see a constant pressure drop. And that's how we will take the hydrodynamic study of the inverse fluidization bed. And after that we will add, as we are treating the waste in inverse fluidization is widely known for treating wastewater. We are treating hexavalent chromium here. We will reduce it to trivalent chromium, as hexavalent chromium is carcinogenic for health and it has very health hazardous. So we will pour we have cultured the bacteria. We will show it now. We have cultured the bacteria. We have now cultured the Pseudomonas bacteria. Then we will you can see here this one. This is the cultured bacteria, which actually we have cultured it, and we have stored it in the freeze. That's where they have settled down, and you can see the dense white color, which is nothing but our cultured bacteria. We take that and we will fill it here in the tank this side, and after going inside the Perpex column, they will form film above this polypropylene ball. Making film in the above these polypropylene balls, they will contact with the chromium and reduce the chromium to trivalent chromium. And that's how the inverse fluidization works, and and why we are using it and how we are using it. Thank you. At first, we have collected the chromite mine wastewater, as we are reducing the hexavalent chromium to trivalent chromium, and we have done a ICP-OS test where we found that the concentration of chromium is 3 ppm, and after the biofilm formation we will keep it for 3 weeks so that it will get the chromium will get reduced to trivalent chromium. And how we will know that the chromium concentration is reduced? We will use the UV spectroscopy. For that we will take sample from after 3 weeks. We will take samples in every 6 hour or 2 hour, and then we will check it in the UV spectrometer, where we can see the absorbance of chromium, and it will and we will can see that there from that we can see that the chromium, hexavalent chromium, is reduced to trivalent chromium by checking the chromium standard from the standard book, which for chromium we can calculate the absorbance of the above that what concentration has decreased in the hexavalent chromium. And we will also calculate this for the solid particles. We will collect the solid particles, and we have taken the BET analysis for that, and after that ESEM analysis for that, and after that we will, to confirm the growth of the microbe, we will see it, and it will show, like ma'am has shown you earlier, a dense particles film is formed above the polypropylene ball. Then we will take, which we, from ESEM we will be able to know that the film is formed successfully. Then we will pour it, then the reduction will also take place.
This is my 3-phase fluidized photocatalytic reactor. Here 3-phase means we are using solid is our catalyst particle, that is CSGSC, titanium dioxide supported coconut shell granular activated carbon, and this is my solid phase. Now liquid phase I am taking, normally for hydrodynamics purpose I am taking the water, for experimental purpose I am taking a dye solution. Now gas phase is what air, so compressed air, that is through filter medium we are giving compressed air or filtered air also we call. Now coming to the point, first of all you have to see the hydrodynamics, 3-phase hydrodynamics, how it is occurring, hydrodynamic study. Now hydrodynamic study in the sense that here what are the hydrodynamic parameters. First of all you have to take hydrodynamic characteristics. What are the hydrodynamic characteristics you are reading? Now hydrodynamic characteristics in the sense that your bed pressure drop, from where you will get the minimum fluidization velocity. From this graph you will get minimum fluidization velocity. Now coming to the point, next hydrodynamic characteristic, that is bed porosity or bed expansion you are calling. Now in this you are calculating the bed expansion ratio, and your bed voidage. Now next one is gas hold up or phase hold up you are calling. Now these are the hydrodynamic characteristics. Now what are the operating variables? Operating variables you are taking here. The operating variables like liquid velocity or superficial liquid velocity you are calling, superficial liquid velocity, and superficial gas velocity or air velocity. Next our initial static bed height, and particle size. Then your our viscosity of liquid viscosity. Now these are the operating variables, these are the hydrodynamic parameter, and for various operating variable you are calculating the hydrodynamic, you are doing the hydrodynamic study of a 3-phase fluidized photocatalytic reactor. Now here you are taking the annular shape in the sense that you are in the middle, you are making an annular region here. In the annular region you are taking the bed material. This is my annular fluidized bed. Now this is now for that what you have to do, suppose your bed pressure drop you have to find out, your effect of bed pressure drop you have to calculate. Now for that what you have to do, how to take the reading. You are reading what? First of all you have to do the liquid flow rate. Different liquid flow rate or liquid flow rate, from the liquid flow rate you will calculate the velocity of the liquid. Now this is manometer reading. Here this manometer reading, 2 limbs are there, left limb and right limb are there, and initially before changing the flow rate at 0 flow rate you will record the reading of the manometer. Then above that how much pressure drop is changing, that you have to calculate. Now this is manometer reading. Next you have to do observation you have to make, means what you are observing, how the particles are moving, how the particles are tilting, or no particle movement, only slight movement, that you have to record. Next, your liquid flow rate manometer reading, then your bed height. Bed height you have to measure. This is the, because from this table itself you have to calculate what are the effect of effect of different operating variables on bed pressure drop, like by changing initially your gas flow rate you are keeping constant, you are changing the liquid flow rate, and remaining all the particles are remaining constant, like particle size, initial static bed height, all the things parameter will keep constant. Now when you will change the different gas velocity, you have to change the flow rate of the gas. Initially you are maintaining the constant flow rate, and for 0 flow rate then you will go for your 5 lpm to 10 lpm, like this different flow rate of air or gas you have to take into account. Now these are the different how to take the observation table in your hydrodynamic characteristics. Now from that you have to calculate the table and graphs, all these things which I have explained detail in the class. Now this is my hydrodynamic study. From this different for bed pressure drop we have done, like by changing various variables, like different hydrodynamic characteristics you can calculate by making the similar tables for different particle size, for different initial static bed height. Now coming to the point, this is my how hydrodynamic study you are making. The basic of the hydrodynamic study already you know how terminal velocity will change, how the what is the fluidization generally. The fluidization particle means the particles behave like a fluid. Now here two-phase fluidization and three-phase fluidization, that different types of fluidization also you have seen, that particular fluidization and bubbling fluidization. Here both mixing characteristic will get, because this is a three-phase fluidized bed, you are getting bubbling at 0 flow rate air flow rate you will get in the particulate fluidization, and at when you allow the flow of the gas you will get the bubbling fluidized bed characteristic. Now coming to the point, photocatalysis. Now photocatalysis, this is the nowadays this is called also advanced oxidation process. Now advanced oxidation process now a burning topic, because maximally whatever the biological treatment or your adsorption experiment, what they'll simply transfer the material from liquid phase to the solid phase. Am I correct or not? From liquid phase to solid phase, because they are simply transferring. Because if by bioreactor, what will they do? They will absorb the material and simply they will store in their enzyme. Now in their body. In case of adsorption, simply what will act? The your pollutant particles will get transferred from the liquid phase to the solid adsorbent. Now here you are facing that adsorbent that is unreactive. Once the adsorbent is used, they are useless, or they have to regenerate, which will add extra cost to the process. If your industrial application you will set up, that will what leads to extra cost. Now in order to avoid that one, in order to decrease the extra cost, you have whatever the cost you have extra you are giving in our industry purpose for industrial wastewater treatment. Now that extra cost will be reduced by means of photocatalysis. This photocatalysis, what will do? It will do what? Simply the convert the pollutant, organic pollutant or whatever the metallic inorganic pollutant also they will convert. In case of organic pollutant, they will convert into simply CO2 and water and some intermediate product, which will harmless. Which is what are the harmful pollutants will get converted into harmless compounds like CO2 and water. These are the harmless compounds. No doubt CO2 is a pollutant, air pollutant, but it is a food for the plants. That's why some books are writing that CO2, if at all in industrial area, that CO2 may be pollutant. But in case of your normal village area, that CO2 is not a pollutant, because the CO2 is a food for your plants. We cannot consider that as a pollutant. Some books is written like this. Now coming to the point, the photocatalyst. When you now I have told the importance of the photocatalyst. Now photocatalyst you are doing. Now photocatalysis are also different methods. Heterogeneous photocatalysis and homogeneous photocatalysis. Now heterogeneous photocatalysis in the means the phase is different. Means you are taking the solid photocatalysis. And homogeneous photocatalysis means what you take the liquid photocatalysis. But liquid photocatalysis when you are taking, what will happen? That ions also, suppose FeSO4, that photopentant process. Photopentant process in the sense, what is the difficult again? Because the photopentant process, that iron content will again increase in the water. and that iron also we have to remove, because that iron certain quantity is required for our body, but more than that, that is useless, and that water again polluted. So that we are moving towards the solid photocatalysis. Now coming to the point, solid photocatalysis. Solid photocatalysis also they are using many more applications they have got, but when they are using solid photocatalysis, fine particles are using, because TiO2, the titanium dioxide nanoparticles they have developed different process for nanoparticles, but nanoparticles are mainly what are the adsorbent, even though, because why you are using nanoparticles or nano adsorbents? Why? Because when you are using nano adsorbent, the surface area will increase, so that the reaction rate will increase, and you will get the maximum removal, percentage removal, or maximum degradation in case of photocatalysis. Because in case of photocatalysis you will call it degradation, and in case of adsorbent you will removal. Now coming to the point, this will, whenever using the fine photocatalytic particle, no doubt it is beneficial. Fine photocatalytic particle is beneficial, but it will create a major downstream process, downstream difficulty. What is that? That is what slurry problem. Because once the water is treated, and that slurry will react. Slurry to separate from nanoparticles from the water is a headache, because you have to high capacity centrifuge is required, and which is again extra cost to the water treatment plant. Next, another sense is that whenever fine particles you are taking, that block the surface of the UV lamp, and that UV lamp rigorous cleaning you have to require, because whenever you have handled the fine particles itself, but the TiO2 nanoparticles you have handled, when you are handling that one, what will happen? That simply they will make a layer on the surface of the glass, and by rubbing you have to remove methods. The different methods, vapor decomposition and thermal impregation, and different methods and thermal impregation, and different methods are there for impregnating or for coating this photocatalyst material on the surface of the inert material, or the coarser material they are taking, that is silica gel, all these things. Now when they are taking that one, the efficiency is gradually reducing. Definitely, because whenever fine catalyst particles they are taking, efficiency is higher, but fine particles they are not taking they are simply coated on the surface of the silica gel, means what, the efficiency will decrease. Now in order to increase the efficiency, what you are doing, the silica gel is simply replaced by your activated carbon, that to granular activated carbon, and that granular activated carbon you are simply what, you are coated, means you are placed layer, not a layer. If coated means what, the adsorbent is useless. When you will coat this material on the surface of the adsorbent, because adsorbent is inside the photocatalyst. Now how that is useful? Because when a coating will make, that coating will not, what they will do, simply when you are preparing the water material, at a particular place they are coating, because you are retaining the characteristics of both adsorbent as well as photocatalyst. Now it will act like both adsorbent as well as photocatalyst. That's why it is called integrated photocatalytic adsorbent, IPCA are calling. Now this IPCA, various adsorbents are nowadays, the adsorbent are different types of adsorbent you are taking, like zeolite, activated carbon, all other adsorbents are coarser particles, because they are moving towards the coarser particle. Why? Because to decrease what are the downstream disadvantages what are there in the catalyst, and while using the fine photocatalyst particle, again only adsorbent. Now this is our phenomena. And now this why you are using fluidized reactor, because fluidized reactor maximum reaction rate or maximum contact between this phase material, or contact between the solid and liquid phase will take place. Again it will increase the amount of dissolved oxygen also. Now why use this air also? Why air is required for photocatalyst? From basic mechanism of photocatalyst, what is that? When you are using the photocatalyst, what will happen? These photocatalyst particles, your valence band and conduction band. Now this valence band and conduction band, when any light source, UV light source or visible light source or sunlight will fall on the surface of the photocatalyst, like TiO2 then all these things, MnO2, these are the different photocatalysts. When you fall on the surface of the photocatalyst, what will happen? The electrons will get transferred to the conduction band, and here you will create H plus ion hole and E minus. Now this is temporary. When you remove the light, again the electron comes back to the valence band. That is called recombination. And this in order to avoid this recombination, because when recombination will occur, what is the use of the photocatalyst? Now, in order to decrease the recombination, what will you add? You add air. You are using the air. You are bubbling the air, or you are increase the dissolved oxygen of the air with the water, so that air will be absorbed by the photocatalyst, and this air will react with your electron. Will absorb the electron to convert into peroxide radicals. Again, this peroxide radical will react with water to form a hydroxyl radical. This hydroxyl radical is a powerful radical. This is because this is important. Hydroxyl radical is in the photocatalysis. Even if any advanced succession process, or even if any photocatalysis process, this hydroxyl radical is important. And this hydroxyl radical, what will happen? It simply convert the organic pollutant into what? Carbon dioxide and water. Now this is the role of oxygen, because oxygen will react with the electron to what? Again, hole will remain. This hole, what will happen? The water, what is the water molecule present in the solution? Because water you are taking water. That water molecule, what happen? Will react with the hole to get your hydroxyl radical. Means the hydroxyl radical production is increasing, and this hydroxyl radical simply will organic pollutant or inorganic pollutant, it will convert into CO2 and water, so that the complete degradation of the pollutant will take place. Now, in case of organic pollutant, complete degradation. In case of inorganic pollutant like chromium, all these things, lead, all these things, they will change into that harmless valency. They will convert what are the pollutant valency, they will convert into harmless valency components. Got it? Now, this is for this reason you are using this is the basic funda of your photocatalysis. Now, what is the use of air? Why you are using air? Because 3 phase because photocatalysis purpose 3 phase only required. Other type of fluid you cannot use, because air is anyhow must required to decrease the recombination rate. Now, coming to the point, when you are using this activated carbon support, some literature I am finding that this will decrease the band gap or band gap tuning. You change the band gap of the photocatalyst, so that the electrons can easily jump from the conduction band to the valence band to the conduction band. Now, the further purpose also activated carbon will add some added advantage to the photocatalysis. Now this is my basic concept which I have used in this concept in your photocatalytic reactor. That is your liquid velocity is 0. When you are increasing the liquid velocity slightly, because this is 0 is indicating. Now when you will increase the liquid flow rate, what will happen? The movement of the particles will take place. You can see here no movement, because liquid velocity is not changing. Here occasionally the particle air is coming, because that you will creating the bubbles, and the small bubbles will not getting the chance, so that they will small bubbles make a great bubble, and they are coming out of the bed. Now when you increase the flow rate, the bubbling will be easier, so that at that time no disturbance will take place. Now coming to the point, when you increase the flow rate again to 5, like you can see the slight lifting of the particles will take place. Slightly the lifting of the particle will take place and start lifting. Here the bubbles creation is increasing nowadays, because initially a large bubble is coming. Now gradually the number of bubbles is increasing, and that is not a constant supply. That's why it is a problem. Now coming to the point, here the bed heights gradually increase. You can see when you increase the flow rate, again you can see the particle. Now the air is getting more energy to come out. That's why it is again helping for increase the bed height of the material. Got it? Now the bed height is here, the lighter, here, this is the lighter particles. Now this height you have to measure, because gradually you can see the height is increasing. Now you have to note down for different flow rate. Different flow rate, what is the, here the fluctuation of the pressure drop also you are finding. Here what will happen, once minimum fluidization is coming, the pressure drop is constant. The pressure drop is constant. Why? Because the low, you can see when 10 and 15 you will see, we can see that this height remains constant. Why? Because there is no change in the pressure drop. Now when I will increase further the flow rate up to 10 LPM I have got. Now you can see when you are 10 LPM, what will happen? This because now fluidization has started. Because the fluidization will start means what? The particle is rising and coming back. That is uniform settling velocity. Because the equilibrium terminal settling velocity means what? The total upward force equal total downward force. That means at that time the particle will move with a constant velocity. Again it will falling back with the action of the gravity. Now like this, that is settling velocity. That is falling back with a constant settling velocity. Am I correct or not? The falling back velocity is not a constant settling velocity. Now likewise the bed height is increasing. Now you can see air velocity and water velocity are increasing. The what? Maximum the rotation of the particle will take place. Now when maximum rotation of the particle will take place, maximum contact with your UV light will take place. When you are applying this photocatalytic application, this maximum contact with the catalyst particle will take place. Correct or not? Now so for that 3 phase is required, because whenever this air also coming, this air bubble also coming means what? They will increase the dissolved oxygen concentration. Increase the dissolved oxygen concentration, so that amount of dissolved oxygen increase and photocatalyst light will increase. Now this is my hydrodynamic study. Now when you will go for your photocatalyst reaction, first of all only those who are wearing the glasses or that watch glass googles are there, you can wear that one, then you observe the UV lamp. Got it? Now when you are using this UV lamp, total dark you have to make, because outside light also sometimes announce the photocatalytic reaction. Only the UV light will affect or not. That you are checking that one, outside light you are switch on. But now I am not doing that one. Here this simply you are checking that how the color is changing. That you will make. Now you can show this one, that because always you have to maintain above the fluidization, so that the particle will always you have to above the fluidization minimum fluidization velocity, so that maximum particle will comes in contact with the light or light source, so that because the photocatalyst is occurring on the surface of the catalyst. When the surface of the catalyst, maximum light exposing, maximum exposure toward the light will take place at more than minimum fluidization velocity. That you will maintain. You can see the bubbling are coming, bubbles are coming, which will increase the amount of dissolved oxygen in the water, and gradually when you increase the flow rate or flow rate of the gas, the particle will comes into, you can see more number of particles. When you will more than that minimum fluidization velocity, when you will maintain, what will happen? More particles will comes in contact with the light source, so that maximum pollutant removal. You can see gradually the color of the solution is changing. because this absorption and photocatalysis simultaneously is taking place. Am I correct or not? Simultaneously taking place, that so that the maximum removal percentage, maximum degradation efficiency will achieve. Now you can see initially the color is gradually decreasing, and that where the color is going on, the color is simply converted into carbon dioxide into water. Got it? This air velocity is difficult to go totally. Okay, like you can see maximum particles are coming in contact with your that UV light, so that the reaction is going on. Now gradually the color of the water will change. Now it will take time. That metals are there, like catalyst loading and effect of air flow rate, effect of liquid flow rate, and effect of initial concentration of dye. Different initial concentration you can change, and your what different initial concentration will take. Then your effect of contact time or degradation time. These are the different variables or parameters you have to study. Now coming to the point, kinetics. Here both adsorption and photocatalysis is taking place, means your adsorption kinetics also will study, and degradation kinetics also study, photodegradation kinetics. Now for adsorption kinetics study, simply you are going for your first order and second order kinetics, pseudo first order and pseudo second order kinetics. Now coming to the point for photodegradation kinetics, Langmuir insulated kinetics. Langmuir insulated first order kinetics we have to study. That kinetics part, next isotherm study also will make. And isotherm also similarly Langmuir, Temkin and your friend with isotherms. Now similarly for here only for photocatalysis only degradation study, degradation kinetics you will study, because adsorption isotherm that is for only purpose for adsorption. For photodegradation only Langmuir insulated equation you are using the Langmuir insulated equation kinetics, and that is for that to first order. That first order kinetics you are applying. That depends upon the different material, because whether it is a second order kinetics or first order kinetics, generally in our cases first order kinetics you are getting, and in case of adsorption you are getting second order kinetics. Now these are all about how you are taking how you are taking the different parameters and different photodegradation kinetics and adsorption isotherms. That too, these are the complete setup of a fluidized bed photocatalytic reactor. Now any doubt, any questions you are having? Any questions? Okay, now this is all about your fluidized bed photocatalytic reactor. Got it? Thank you.